So time is just before 10 o'clock. So let's begin. And I prepared some words and phrases for the welcoming messages. Uh, the guests and speakers and faculty colleagues and students, on behalf of the Seoul National University Brain Imaging Center, I warmly welcome you to our inauguration symposium. Yeah. I'm Sang-Eun Lee, the center's director. 안녕하세요. 네. Our center is honored to host a distinguished group of international scholars from the leading institutions in the US, UK, Germany, Japan, and of course, Korea. Your presence today highlights the significance of collaborative research in deepening our understanding of the human brain. Today, we come together to celebrate not just a new facility, but also the start of a more collaborative era in MRI brain research. The installation of our new state-of-the-art MRI machine developed through the Human Connectome project marks a significant advancement in our research capabilities. This advanced technology will open up new opportunities to examine the detailed structure and function of the brain more thoroughly than ever before. In this sense, more than just the advanced hardware, this instrument serves as an invitation, an opportunity to explore broader questions about the brain structure and function, to develop and test innovative process sequences, and to connect methodological advancements with the applications in cognitive and translational neuroscience. With this scanner, we can expand spatial and temporal limits, improve how we measure neural signals, and speed up translational research that could ultimately benefit human health and life. Over the next 2 days, including today, we have an engaging program lined up featuring a wide array of topics from advancements in MRI technology to exciting discoveries in cognitive and clinical neuroscience. We'll listen to leading experts, join stimulating discussions, and foster meaningful conversation that I hope will inspire new ideas and collaborations. I thank my colleagues, the core faculty of our center, for organizing this wonderful program. Our aim for this symposium is to promote lively knowledge exchange and explore new research advances and strengthen our international research community. I invite everyone here today to participate actively, ask questions, share ideas, and find collaborators. These interactions are essential for progressing methods, verifying findings, and discovering new emerging directions. Finally, I want to thank the many people whose dedication made this center and the symposium possible. Our engineers, faculty, staff, students, and our partners here and abroad. Your commitment fuels the science we pursue. Thank you again for joining us. I look forward to days filled with engaging science, meaningful conversations, and new connections. Welcome to SNU and the Brain Imaging Center. 고맙습니다. 네. Now I hand over the microphones to the moderator, Jong-ho Lee, who organized this symposium.
Okay, hello everyone. This is Jong-ho Lee from Electrical Engineering Department of Seoul National University. I'm very excited to, moderate this session. And our first speaker is the famous Gary Zhang. So I don't know whether you have ever seen this video clip of, the Harrison Ford showing up to the podium, and then the theme song of Indiana Jones plays, And then it says, "Oh, damn song followed me all the time." And when I see Gary, that's a very similar, like impression that I want to ask you about Nodi equates to Gary, and how do you feel about this? The technique of Nodi, and you probably have a lot of action of it, and then it follows you throughout your career. And I'm pretty sure that we will hear about this technology today as well. But still, I believe it's a charm that I found, really exciting and happy to see how diffusion has transformed by this technology. Just a brief introduction of Gary. Gary did his PhD in 2007 at UPenn, where I got the connection with him there. And then he moved to UCL, and now he is the center director of the neuroimaging center at UCL, and where he's been developing this NODI technique and more uh, with his team. And one thing that I really, really envy him, and also every time I look at researches, and that's the direction that I want to go, is if you look at this Nodi paper, it has been cited 4,000 times, a single paper. So that's, I believe, what you are supposed to as an engineer and scientist if you are, graduate students or postdoc here. So with that introduction, please welcome Professor Gary Zhang.
Thank you so much for such a kind introduction, Professor Zhang Hou Li, and thanks, Professor Sung Ho Lee, for inviting me to this great occasion. It's a great honor for me to be here. It's the first time in South Korea for me, so and I think I'm always looking forward to be here. So I was telling Jiang Ho, last night I was in London coming here. My plane had a problem. He didn't tell me what was the problem. We were left the gate. We were stuck on the taxiway for an hour before they told us we have to go back to the gate. I really felt I'm going to miss this trip. Luckily, I'm here, so I'm really lucky for me. So hopefully, I'll enjoy this occasion and share some my experience to you and about my excitement of this particular system, which I think is a dream for us as a community doing microstructure. Okay, so the topic of today is that being asked to do is really thinking about how can we taking advantage of this amazing scanner to understand tissue microstructure, okay, in the brain. Okay. So just to make sure we're on the same page, so let me just make sure everyone knows what I mean by tissue microstructure and why it's important to study them. Okay, so this is a very classic example of one of the reasons why we're looking at microstructure and what do we mean by it. So in this picture, you have, I don't know if people can see my cursor. Well, anyway, I'll do without. So in this picture, there are 4 different microscopic pictures of different transgenic mice. And this is what I mean by microstructure. Structures have micron length scale. So you can hopefully see in the top left panel, you have a little vertical bar, and that vertical bar represents about 10 micrometers. So that's a scale we're dealing with. And that's what we mean by microstructure. And that scale, we can look at the different cells. And you can see from the bottom right, which is a mice that's completely wild type normal, as moving from to the top right, where you have introducing 2 copies of bad genes, to the 4 copies, bottom right, bottom left to top left, or 7 copies. These different genes that's causing damage to the myelination to this animal, you can clearly see the changes in the microstructure. So that's one of the reasons why this information is very important to understand, in this case, what we call the gold standard of disease process. And in fact, that is not just for disease process, but also for other things, such as aging. So this is an example that's looking at in the Brodmann area 10, which is a part of the frontal brain region. And if we look at individuals in that region, under 50 years old, this is their dendritic tree structures of the neurons in the gray matter. And you can see very nice branching structure, very dense branching structure. But if you look at people who are over 50 years old, and you can see quite a dramatic change in the level of dendritic density and branching compared to people who are under 50. And so that information can give us some clue understanding how we age and possibly also affect other aging-related disorders such as dementia. And for people here who are doing, interested in neuroscience, and I think what we believe, the similar structure we're seeing here also reflect different functional region coordination. In this case, we're looking at regions from low integrated regions versus high integrated regions. And you see very similar changes or differences between different regions in terms of dendritic branching, which is a kind of signature of the function they want to study. And another example, which is something that I've done work on recently, looking at the visual cortex, looking at the remodeling visual cortex. And this example where we use mouse models, where the mouse are being, when they're just born, their eyes was essentially being sealed so they can deprive of the light stimulation. And we can look at what's the effect on the brain structures. And what you see here on the right, you have two different columns. On the left, you see a normal dendritic tree structure in the visual cortex. On the right is represented a group of mice that actually have been deprived of light stimulation. And you can see, zooming picture in the middle, you can see a very different dendritic, we call spine, tiny little dots that growing out of the dendrites. So that's changed. There are less and fewer spines in the brains of the mice that has been deprived from the visual cortex of vision. And that is something very interesting. And can we study that? And of course, I know that there are a number of psychiatric study topic tomorrow. So I think I also mentioned that even in psychiatric disorders, you also have fundamental brain structural changes underpinning these disorders. And that's a very detailed study of how the cell type and cell shape are different in different disorders as well compared to the normal control. So that's what I mean. I hope I convince you this is something very interesting and important to measure. Now the question is, how can we make this measurement? Well, like all MR, I think people in MR for a long time, we know that it always starts with the story of it's a confound. Okay, and I was, in my abstract, I mentioned that this is something that traces back to maybe 6 years from today. But in fact, you can see that's 75 years. So the very original story starts in 75 years ago. And actually, that's a birth of what we call sequence, pulse sequence. In fact, Irvin Hung was the father of pulse sequence we use today. And that was NMR, now with MRI, but it's very much the same, the spin echo. And he found out that the measurement he was making on the relaxometry, they were slightly not quite right. And the reason he demonstrated to do with self-diffusion of liquid molecules. And that's led to about 5 years later, I believe, that was, about 5 years later, the famous Carl Purcell for the CPMG, people who know the CPMG sequence, this is a CP, who actually look at how we can measure the diffusion for the first time and also give birth to the modern version of spin echo. Okay. And later on, this is what I call the modern version of diffusion sequence, which is also about 10 years later. So you can see things, one mentioning partially that this is how technology really evolves. And I think often, when you're graduate students, you obviously will want to make a difference. And I think I always tell them, you need to be patient, okay? Science sometimes works in different ways. And I think, we need time to accumulate evidence. So in this case, it took 10 years for that technology to be actually used to make really better measurements. This is a Stesco-Tanner sequence that we use for almost everything we do for diffusion, and that's when. And they had the insight that rather than having a gradient, which is we can't even imagine why we would do it. So they have the gradient on the whole time in a Carl Purcell version. He had the idea, why don't we turn them into pulses? That's the burst of pulsed gradient, the notion of pulse gradient, and the burst of pulse gradient spin echo. So that was literally 60 years prior to today. And we're still here. And it also then takes another 10 years, getting my math right, actually, no, 20, I think 20 years later, we finally have that technology to be brought into imaging. Okay, and this was a radiology paper in 1986 where the famous, truly famous Professor Daniel Lebihan, who is the father of diffusion MRI, which is where the eye, we add eye to the NMR where we can do imaging. So the two abstract on the right was in 1985. So that's exactly 40 years ago from today. And then it took another 5 years for the technology that we use today, which is a EPI, using echoplanar imaging, which is important for being able to do this in a very short time scale that we can actually tolerate for most of us in a scanner. So that's pretty much by then, 1990, that's when the modern version of diffusion MR sequence underpinning everything we do today are truly born. And the reason I want to mention this also because one of the key things, if I want to get my animation right, this is kind of links to the topic today about the scanner that your center is actually going to invite you to try, which is one of the key for all this technology can happen is the technology. In this case, another innovation of being able to deliver the gradient performance that's required for this technology. So the first example is the EPI technology was actually invented in 1977 by Sir Peter Mansfield. But I was never really able to deliver real-world benefit until the gradient performance. Some electro engineers able to work out how to make it happen, how to do the shielding, etc., was allow that gradient to be brought to the bear to create EPI sequence. And today we're going to hear about, how that can be benefiting the future of diffusion MRI with this further advances at CMX. And last thing I want to mention, obviously the probably the most famous diffusion sequence, diffusion model, I shall say, is the 1996 by Professor Peter Basser on the diffusion tensor imaging, which is I think hopefully most of you have heard about and being used across the world by many, many groups and institutions. And so I'm going to take a few minutes now to actually tell you about how it actually works, hopefully with a goal to really try to illustrate how gradient play a role in all these processes. And apologies for people who know these very well, but I'll do it in a way that hopefully interesting. So the first thing I always say is actually there's a two-part story. Number one, it is tissue microstructure can be influenced by water diffusion. That's the first thing. That's first thing in this story. And I will show that give you a tour of UCL. So this is London, and you can see we zoom into, that's a front court of UCL. And usually in September, when student graduates, you will imagine people having a celebratory drinks, and that's what they'll be wandering around after that, okay? And that's very much, we call it the random drunkards, okay? And imagine there's something here at SNU as well. But imagine, let's imagine the experiment where we put them in a different spot. So that's a one main traffic road next to UCL. But if you imagine putting those people there, obviously police won't be happy, but that's the pattern you expect to see when they were kind of moving around. Now there is a crossroad here near UCL. Actually, there's a pub at the corner. So actually, this is the real thing. So you can see if you put people there, actually, when they're there, after a while, that's the pattern you will see, okay? And that's essentially showing you the relationship between the structure within which the diffusion occurs, okay? And I'm going to start to fade away the map behind it. And the story is very simple. Now, if you are presented this pattern of diffusion, could you make inference about where they were moving about? And I think in some extent to qualify, yes, we can do that. And that's a story about using diffusion to probe tissue microstructure. Okay, so similar thing in the brain happens as well. So let's just look at that example more in brain. So this is in the ventricle where we have largely just free water diffusion. And in this case, the picture showing you on the top left is a simulation of the diffusion process. At the very start, so all the molecules will be at their original position. So what I'm visualizing is the distance they have traveled from their original position. Of course, the time, a starting point, they haven't traveled. Therefore, everything will be at the origin of that graph. So as they start to diffuse, they're going to be moving away from their initial location. So we call that displacement. So what you're seeing on the top left will be the displacement distribution for all the molecules I'm simulating as they evolve over time. Okay, you get this very expected, what I call a Gaussian distribution, and that Gaussian grows and grows. So looking in detail, looks like this. So a nice way to see this, if we draw a line through this distribution and asking the question, what if I project that displacement along that line? And it's no surprise, it's a normal curve. And importantly, so the mean of that distribution is 0, so it means that there's no flow. So I think people doing flow, I think there's a talk later about flow, so that's different. So we can tell flow from diffusion by looking at the mean displacement, in this case 0, so it's pure diffusion. And then the width of distribution now is a time-dependent quantity, and it's proportional to time, and the proportionality constant is what we call diffusion time. So essentially, we're looking at how fast this, the width changes over time. And in body temperature, in human or in animal, that value in free water is about 3 micrometer per millisecond. So micrometer is appropriate units for looking at microstructure, and millisecond is the time scale we'll be observing this diffusion process. And we call this diffusion isotropic because if we took another direction or any direction, you will see the same shape, same Gaussian. Now, if we look at a more interesting place, such as gray matter, and you see a somewhat similar pattern, but also quite distinct, because you see the spreading doesn't happen as fast. So therefore, you can deduce that diffusivity is slower because of the presence of membranes. But it's also similar in the sense that it's isotropic. Doesn't matter which way you look, it's roughly the same. And here, the diffusivity is about 1 micrometer per millisecond, about a third of the free water. Things get most interesting, which is the success of DTI, is in the white matter, where the diffusion are preferentially happens along the axial direction, and less so when they're trying to diffuse perpendicular to the axons. Okay, and if we zoom into that a little bit, and in the direction that's parallel to the axons, you get still more or less what I call a Gaussian diffusion at a slightly reduced diffusivity, about 2 micrometer per milliseconds. The real interest is on the other direction when we're looking perpendicular to that. So no longer what you're observing is a Gaussian distribution, more like a top hat distribution. And that is a hallmark of diffusion are being restricted. So there are water molecule cannot moving across the membrane, in this case often to do with such as the presence of myelin, as you probably will hear from Professor Jung-Ho Lee in his talk. And in this case, the diffusion variance, the spread of the distribution now is a more complex function of time. In fact, over time, that diffusivity approaching 0. For most of the practical experiment we do with the kind of imaging system prior to the CMAX, that's pretty much the fact of life. And I think, as I'll explain, we may change that. We may start seeing that time dependence with advanced systems such as CMAX. And finally, the most interesting thing is we have multiple crossing fibers in the voxel, so you get that nice crossing picture. And that's one of the most successful applications of diffusion imaging for understanding the structure connectivity in the brain, for example. So the nutshell says is, as I showed using the UCL example, the patterns of diffusion displacement distribution is highly sensitive to tissue microstructure. So if we can measure that diffusion displacement, we will be able to get ability to potentially infer back the tissue microstructure that underpins that displacement distribution. So how do we do that? Okay, I'm not actually going into any of the physics, but I'll try to review just enough that you need, I hope. So what we need to do first to get up and close with those pulse gradients for a second, these are what we use for sensitizing the diffusion. And what you see at the bottom is a stripped down version of what we call pulse sequence, which is basically a set of events happening over time. So I strip away all the other elements I don't think necessary now. So only revealing this, the first pulse. We use two usually. So the first one you're showing here. And so it has two features, actually three features. You see two. One, it has certain width, we call duration, how long the gradient needs to be on. And second is how tall or how strong, or the strength of the gradient, which we call little g. And the third is the direction. So that's a little red line I showed you in the previous slide. That's what I mean by we can choose those direction with the gradient. And what their job is to essentially pinpoint, tagging the initial positions of each spins in your sample. Okay, so this is essentially equivalent to this picture where we know where people are. What do we mean by the zero displacement at time zero? And that's the direction we're referring to. Become more important than x. So then, a very important point here is for this to really work well, the delta, the duration of the pulse need to be small, and that's important, and that is not generally true, as I'll show you later, but I just want to highlight delta really meant to be something small so that we can localize very quickly, because otherwise the diffusion would have happened during the width. So you can't read the initial location is kind of being corrupted by diffusion. And then what you do is in Susquehanna scheme they proposed, they fire a second pulse, identical in every other way except a delay of some time we call big delta. And that's a proxy for diffusion time, how long we ask the water molecule to diffuse from the initial time. And same direction, same duration, same strength. And this second pulse allows to encode the precise position of the spin after the diffusion period. And that's allow us to essentially have a picture of that displacement distribution we've been talking about, okay, as I showed you before. And as I mentioned, when delta is sufficiently small, the diffusion time basically can be represented by the spacing between these two pulses. Okay, so in summary, the standard diffusion sequence has this essentially 4 key parameters: the duration of the pulse, the strength of the pulse, the direction of the pulse, and the spacing between pulses. Okay, so these things are collectively allow us to do a lot about measuring this diffusion sensitivity. And just to give you a concrete example here, to see how the signal evolve as the displacement distribution changes. So when initially, or the diffusion time is 0, then in fact that's a baseline signal, means there's no diffusion. So you see on the top is 0. And in this example, I use a previously, actually before SIMO-X, is a unachievable gradient strength of 100 millitests per meter. Just for reference, the typical system has a maximum gradient strength with Prisma, for example, state of the art, before SIMO is 80 millitests per meter. So that example I created probably 10 years ago now. I think we don't even have here Prisma. We only have up to 60. Okay, so that's already was a bit of a fictitious example. And I use this fictitious little delta, the duration of the pulse of 5 milliseconds, simply not achievable with the system back in the days. Okay, and with a chosen direction, so if I monitor as I prolong the diffusion time, and without giving you all the equations how that happens, but you can just trust my my knowledge that the signal will start to reduce. That reduction is, as you can see, is exponential decay. And the rate of the exponential decay is something that directly related to the diffusivity you want to measure. And in this case, because it's isotropic, so if you pick a different gradient direction, you get basically the same similar pattern up to the noise. So I'm not plotting noise here. Okay, and you can see if I look at the same thing for the 4 example I gave you, not only CSF, gray matter, white matter, and white matter with crossing, you get this quite a distinct picture. And that's the reason why measuring this signal allows us to tell the microstructure apart. Okay, and in practice, what we normally do, you know, in the DTI, for example, we pick a particular diffusion time and makes a measurement. You can see that even with that single time point, you more or less can tell different tissue type apart, and that underlies the success of diffusion tensor imaging. Okay, so precisely what is the role of gradient strength then? Because what I show you here, all you see is the diffusion time. As I change in diffusion time, signal decay, and I mentioned to you that relates to diffusivity. But where's gradient strength? Okay. Go back. Okay, that's what we try to, yeah, so let's look at this picture again. And under the assumption that diffusion is Gaussian, we end up with this. Hopefully, I promise you this is one of the two equations I will show you, because it summarizes the process more elegantly. So on the left is a signal we measure, and I have two groups of variables. I ignore the direction, so on the left you got gradient strength, gradient duration, and gradient separation. These are the settings we choose as an experimentalist. On the right is D, which is a variable of the property of the tissue we're trying to study, we want to measure. And that signal is proportional to an exponential function, which has a few components related to both the property of the sample and the property of the settings. Okay? So one of them is the diffusion time, which is when delta is not negligible small, we need a slightly correction of big delta by a factor of small delta by 3. So that's the notion of diffusion time. That's how long we observe the water molecule diffuse. And of course, the D is a property of the diffusion. And as I mentioned that, as we increase in diffusion time, and the curve is decaying exponential decay, that's very simple. So the rate of diffusion you can see are controlled by the D and the actual thing we call Q value. For people who know, it's a Q space imaging originally, when delta is sufficiently small. And that Q value together with multiplied with D give rise to the slope of diffusion, slope of the decay. And this really underlies the importance of the gradient strength. Imagine a situation where the D, the diffusivity, is very small. What would happen? That means that when D is very small, the decay rate might be very small. So under the noisy situation, you may not be able to tell the decay from noise. So this is where G comes into play. I can compensate by the small d by amplifying G, so increasing the coefficients of decay again, so make that decay more apparent, and above and beyond we can measure with noise. So that's really the role of G. Okay, and importantly, the G can function in a quadratic fashion. So if you double the G, you get 4 times the benefit, okay, in terms of how much influence you can get. Okay, so in summary, the take-home message for you to remember, what is G, the gradient for? It's the magnifying glass effect. Okay, so by having better G, you can actually see things clearer with everything else under the same control. And that's one of the reasons why having a system of sigma x, and I think we more than doubled compared to Prisma. So we're getting a benefit of more than 4 times the benefit in terms of the ability to magnifying the diffusion process we want to prove. Okay, so that's hopefully that's the punchline of my talk so far. Okay, but this is also giving you the opportunity to introduce something many of you might heard about before you heard this, is the B value. And that's what B value is. B value essentially are the multiplication of these things. And the second message I want to give across today is to you that not all B values are equal. Okay, and in fact, B value has been served us very well, because it's when we're describing our paper, describing our acquisition, we just report B value. But there are a lot more behind the scene. Hopefully I explained to you the B value are controlled by the gradient strength, the gradient duration, and the separation between pulses. Okay, the big delta is very important because that is controlling what physics we are measuring, the diffusion we're measuring. While G and delta together is more of a magnifying effect of what we're observing. So they're very different roles. And by using single value B, we are mixing all this information together. Okay, so that's one thing I want to mention. So for example, this is a picture we can get with maybe a very advanced system, but we can do the same thing with a less advanced system that look like that. And these two have the same B value, but they're really looking at very, very different physics. Okay. And which one is possible, or what is possible, depends very much on the maximum gradient strength available to us. So looking at this, say the Siemens trio example, say the 40 millitest per meter world, well, the top is the only thing we can imagine. Okay, that's all we can do. The bottom is simply not possible. Okay, as I mentioned, really to do it right, we want delta to be small. Well, delta on the top is far from small. It's almost equal to big delta. So it's a big, big issue, and that's the only thing available to us, unfortunately, in the past. And now, today, we have a system which is 5 times strong, and we are now able to do both. And that's really opened the arena to what I call the new frontier. Okay, so even though I say that bottom probably is preferred, but nevertheless, the top gives us something different. So with a sigma x type of system, we now can navigate the space from the choice of little delta, choice of big delta, looking at different physics. We can navigate that space and collecting data that we simply not possible. Okay, and that's one of the reasons what I say this is a new frontier. Okay. Now I'm moving gears. So in the sense that, why someone like me here? Better data is obviously fantastic, but we need to know what to do with it. So hopefully I'm going to make the case for some of the stuff I do that Professor Jung-Ho Lee mentioned earlier. So, going back to these pictures, and you've seen it, you know what they are. And what I want to highlight is, in these slides, number one, top left picture is Gaussian. Okay, if I ask you to tell me which one of the rest are Gaussian, I don't know what you think. Well, I'll tell you the answer. This is definitely not Gaussian, I showed you already. And if the single fiber is not a Gaussian, probably crossing fiber definitely not, indeed. And surprise, surprise, even the gray matter is not Gaussian either. So none of the structure of any interest to us are not Gaussian diffusion appropriately modeled. Okay, so really, kind of the message DTI, as popular, as sensitive as it might be, it is not the right model for the process we're measuring. And as a result, it can give us what I call surrogate quantity we're seeing, but not directly measure those features, such as the size of axons, the density of axons, etc. And that's, we need to do more. And that has been my research for about 15 years. So what we really want to go after is the bottom, these histological features, those microstructures I showed you at the start of the talk, like cell size, shape, density, perhaps even membrane permeability that a sigma x system will allow us to start to probe by changing diffusion time, and orientation distribution. And we're going to do that through the signal we measure using systems like sigma x. And what we need is to be able to take that signal and estimating the bottom. And the approach we have to do is to take a modeling approach. We have to build a model from the bottom to tell us what kind of signal we expect and compare to the signal we actually measure to achieve what we call the virtual histological analysis of the data. And this is not possible without a model-based approach, which I hopefully will illustrate next. So I'm going to illustrate one example, which is a classic, what we call in our field, compartment-based diffusion model. Using a simple simulation framework, in this case, a bunch of parallel axons, really simple examples where we think about white matter structures. And it's a bunch of cylinders, which are at the bottom show the cross-section of them. So the water molecule can be either dancing around outside or I'll come back. So then, they were behaving like that. So this is actually what we call extra-axonal diffusion. It's very much a Gaussian-like. And then there are also the one that's trapped within the axons. And they are very much what we call the restricted fusion. Okay, so in contrast between the intra and the extra-axonal, in the directions parallel to the axons, they're very, very similar. Okay, they're nice Gaussian. But in the perpendicular direction, on the extra-axonal remains Gaussian, but a bit narrower distribution. On the right is strictly a top hat picture, especially if the little delta is as large as what we have been having to tolerate with the lower maximum gradient strength system. And so the left is what we call restricted diffusion, and the right the hindered diffusion. And of course, you can see that they're very, very distinct. So if you were, in an ideal world, can actually label this water extra and intra, and it can measure them separately, that's what you get. You can see clearly they give you very different signal. Okay, if I can measure those signals, you get very distinct mono exponential decays, but very distinct ones. So by a single DTI type of measurement, you would tell them apart. Okay. And of course, we do need to pick a single chosen p-value, whatever that is. But the problem is, actually, we can't label them as such. We can't actually tell there are two of the same water molecules. So we only get to measure their combined signal in the middle. And that lies the challenge we have. And how can we actually disentangle that? If we can, now we can actually tease apart intra and extra. Therefore, we can measure how much water in the axonal structure, how much is not. We can measure axonal density, for example. And how do we do it? This is where we must use modeling, which will also require assumptions. This is already a very big assumption. This is assuming parallel axons, straight axons, which is not really true in the real world, but that's something we have to do. This is where how modeling works. And yeah, so we take an advantage of the fact that combined signal now has to be a multi-exponential decay, which means that to be able to detect the signature of multi-exponential decay, we must choose multiple p-values. Okay, a single one no longer valid. A multiple value is essential to do that. So often we do 2, sometimes now we can do 3. And this is also explains why we need a system such as sigma x. You can see to be able to choose these two p-values, we need them to be sufficiently apart. If they're too close, they're looking at the same thing. Okay, you need it far apart. But the one that's a larger p-value will decay the signal more. Okay, so when you decay signal more means that you are getting that measurement closer to the noise. And we need a system that allows us to achieve that p-value while not getting into the noise floor. And a system such as sigma x will allow us to do that, which is simply not possible before. Okay, I won't quite explain the reason, but you can discuss later. Okay, so in summary, what I'm hoping to show is to go beyond DTI, we need be able to do modeling and having data. Of course, the sigma x help us get that data, and jobs, people like myself are working to develop the right model for this. And I'm just quickly going through that with a Noddy example. Just quickly check where I'm with time. Okay, I should probably wrap up soon, but a little quickly. So yeah, this is actually thanks to some earlier work by a professor from Denmark, Sune Jespersen, who look at this in animal model, and I'll ignore that for a second. So what he's shown, which is later on that the measurement he can make using the diffusion MRI technology is highly related to what you get histology. And so my work, this is a naughty work that Professor John Lee mentioned, is very much inspired by that, thinking about what can we do to take that preclinical system results into the clinic. And that's what led to this piece of work that I've been continuing on to today. So I'm going to the details. So the technology allows to measure white matter and gray matter. Hopefully there's some. So this is what I consider a voxel looks like in the brain. It has tissue space and free water space, such as partial volume with ventricles. And the tissue space also being further divided into intraneurite space, or intraaxonal, intradendrite space versus extraneurite, due to the distinction in the characteristics of diffusion I showed you earlier. Okay, and then the signal we measure is really a combination of these three factors. And because each of these components are highly different, this allows us to model the contribution from each and then disentangle each of the relative proportion. And so this is a very different from the earlier view from DTI, also the subsequent DKI, where we really only get a single composite view of the signal. Okay, instead we are disentangle them in different constituent parts, and that's one of the strong motivation for us to do that as a community. And just to summarize, so we can measure things like free water fraction, which is basically amount of water relative to the rest. And we can measure neurite density index. This is a measure of the tissue property, how much within tissue are occupied by dendrites axons compared to the extra-axonal space. And finally, how the dendrites axons actually are arranged in space. We call this orientation dispersion index. And here's an example. It's actually a picture of my brain 10 years ago now. And on the left is what you get with DTL, on the right, which get Noddy. Just to highlight one example. So what you see on the left by the FA, which is a region which often used for DTI, often said is a measure of wire matter integrity. Well, if you look at it, there are some holes, a dark spot in the middle. Is that because of I have some neurological disorder? Well, thankfully, Naughty tells me no. In fact, what happened is you can see the neural density is nice and flat, okay? Similar, no holes. The holes, the so-called quote-unquote holes in FA, very much to do with in ODI have different dispersion, okay, as we know, different crossing pattern, okay? So it's very important. What we're offering with Naughty is we can disentangle the various biological factors that explains FA, but actually tease them out from free water can reduce FA, crossing fiber reduce FA, lower density reduce FA, and with Naughty we can tell them apart. That's one of the reasons why we do it. And this is one of the few technology we're also able to validate in histology. So here's an example in the MS lesion. We see a reduced ODI, which is actually quite a surprise result by our neurologists. But it was exactly the same in histology. And they realized what happened. What happened is in the lesion, some of the dominant fibers are being destroyed by the disease process. Remaining fibers are less coherent, for example. I think I'm running out of time, but just quickly to say this is a protocol what I normally would recommend for Prisma. The detail aside, this historically take about 15 minutes. Tolerable. Thanks to the multi-band technology, we can reduce it to about now 5 minutes. And also get a much better resolution, 2 by 2 by millimeter. So I was very happy when I can do that. But now with the CMX, we can really push the boundary where we can do the same thing the same amount of time while reducing the voxel size by half if you look at the volume measure. And that technology was done on HCP for people who know HCP, but that scan takes 30 minutes. Now you can do it in 5 minutes without losing SNR. Actually get better, so I would say. And just I won't skip this. Just breathe through some examples. So this is one of the early one looking at using Naughty to look at relationship with human intelligence. Naughty was used in the UK Biobank, and it turns out it was one of the marker truly stands out in terms of associating genetic association. And in this case, diffusion stands out among all the others as well, where my arrow shows. One of my recent work with a group in the UPenn, we're looking at using Naughty to measure the brain remodeling as a consequence of the visual recovery among this group of individuals who suffer from genetic visual deprivation, but gene therapy brought the vision back, and we can actually see that change in the brain. So this is a structure in the visual cortex we're looking at, and we can see over time the changes in the visual cortex. I won't get into details. And more recently, we published with my collaborator in the US, we published a review looking at how Naughty is used in various psychiatric disorders as well. So I won't go into the details. So I did promise AI. I know I run out of time, so I'll very quickly. So I think it's relevant for CMX. Is what we need AI is to enable inline post-processing of these technologies. So there are two components which are very time-consuming with diffusion. One is distortion correction. And we recently published a paper to do that with deep learning. We can do that in seconds. So that brings it possible to integrate into the scanner. And second, to actually make the model fitting to extract the Naughty parameters fast. Historically, it takes hours. Hours is underestimation. It's about 20 hours for a single brain. Probably even more with a dense small voxel today. And now we can do that in seconds. And crucially, we're working with colleagues in Siemens. We're now taking advantage of the so-called Onyx integration, or with Open Recon framework as well, that available on CMX. We can actually bring this technology directly onto the scanner, which I think is a future that CMX will be make it possible. So it's probably quite hard to see that picture, but that's very much the vision what we would like to. For people like me and Professor Jung-Ho Lee, we would love to bring our technology into the scanner, and I think this type of innovation that Siemens brought on to the community will be really greatly appreciated. So with that, I'm going to quickly summarize. Hopefully I showed you diffusion MR is unique, give us unique access to tissue microstructure, and the maximum gradient strength is really the key performance enabler. And we have a transforming technology machine available to you, to your community. And importantly, even more so than ever with the Siemens type of technology, not all p-values are equal. And hopefully very much encouraging our Siemens colleague, not just give us a p-value, but also give us other things because they're really important to know. And hopefully also convince you to take this, to make the most of this information, we need modeling, okay? With the right data and modeling. Node is just an example of what we typically do today. There are many other things we are working on. And finally, just thank the founders for their support. And thank you for your attention.
I can start with one question. So one of the challenge of this modeling is always in the validations. And every time, from my experiences, every time I come with this, validation, they ask for more, they ask for more. What was your approach of, convincing people of your model to be accepted in the society?
It's a challenge. I think we have to, accept as a community, which I think MRI is complex. It has affected by a lot of factors. And I think we as modelers, we make our picks, of course, because of that, something we know how to handle. There are things we can't handle, so we sort of ignore them and put them under the carpet. So that's all true. But in practice, which I think that's where MRI is very valuable, because despite those imperfections, when we bring them to the hands of clinicians, neuroscientists, and if we can help them to answer the question they're interested in a way that's better than they can before, and that's a step forward. With all the caveats, of course, we have to acknowledge. And I think that's kind of my approach. And I think one of the things about the NODI, among other models, it's not a better model, certainly not a worse model, but not a better model, I would say either. It's just that it's a model that I made it available to the community for the first time. I think NODI is the first model that I made the source code available for people to use. And that has really let it take off, okay? And that's important. And of course, the second thing is also time, which is when Prisma system become available. This all kind of coming together. And once it gets to the hand of the users, then the experience gets built, knowledge base gets built, use case being built, we get to learn about it, which I think, science doesn't work like a, like a bullet, you know where it's going. It's more like a diffusion. So I think sometimes we just need that patience and providing our tools to make them available to be used. And over time, the winner will show up. And it might not be my model, and that's really not the point. The point as a science community, we want to enable the right one eventually emerge. So I think we just have to make our own contribution in that process.
Thank you. Any other questions? You need more coffee? So, okay, please.
So thank you very much for the great talk. About the Gmax. So increasing the Gmax give us more better in diffusions, increasing more. Like now, commercial machine give us a 200 Gmax. And some research machine for the head gradient give us a 500 or something. So increasing Gmax give us better and better in the diffusion-weighted image.
Oh, certainly, absolutely, yeah. I think so. Obviously, I don't have the data to show you, but if you're being an expert in MR. So one of the reason, I think, if I can go back to, I didn't really kind of bury under the carpet. If I can go to that diagram, yeah. So what's not being shown in the pictures are the spin echoes, RF pulses. You got a 90-degree pulse and a 180 pulse, and then the echo where we're going to make the measurements. So if you want to get better signal, you need to keep your echo time short. Okay, and if your sequence looks like on the top, you have a problem. Okay, that limit how short your TE can be made. So with a very strong gradient, you have the ample space to reduce your TE, which is gave you the baseline SNR dramatically boosted as a result. And that has been the Achilles heel of the community, really. And I think the kind of advances we were able to do, to show you as an example. So the study, sorry, it's going to take a while. This animation is nice, but it's not very good when you're doing forward. Which example I'm talking about? This example, for example, yeah. So this one is actually quite a challenging study to do because of, we're looking at a group of individuals undergoing gene therapy. It's a very rare disorder. So we have about, you can see 10 individuals, and the signal is noisy. Okay, and that's a lot come from basically the diffusion technology or noisy. This was done on one of the 40 millitest per meter machine. So this is one of the wide bore machine. I forgot the name it is called. So Noddy was quite a challenge to implement on that system. But today, I'm absolutely confident by having the superior SNR. I think together, I didn't mention, say, deep resolve, which is also have a profound denoising effect. We are going to be able to make these measurements much more accurately, and we're in a much better position to take small effect. Yeah.
So, well, thank you very much. So another questions about the microstructure in the gray matters. So in terms of the such aspect, so higher B value give us a better information from the DTI or diffusion imaging.
Yes, absolutely. Even more so. Let me find a way to. Don't know if I can't. Like I just. Unfortunately, I can't. I have to go back. So this is even more relevant in gray matter. I think as my picture earlier showed, the gray matter decays. So if you look at the top right, that's for gray matter, and bottom left for white matter. For white matter, along the fiber, it's obviously decay very fast, but perpendicular to the fiber is actually decay slow, meaning that we got a lot of signal. So gray matter will lose signal very, very quickly. And having a big gradient, shortened TE, give us a much better chance to measure gray matter. That's number one. Number two is the modeling, more profoundly from the modeling perspective. So if we able to tweak the diffusion time and pulse width, and one of the theory in our field is that probably for gray matter dendrite, we may need to model permeability of the membrane, unlike white matter of the myelin sheath. So therefore, especially when we have a long diffusion time, maybe we'll have water molecules going in and outside the membrane. So we will be able to start to get a handle on that from data perspective by have the diversity of different encodings from fat to sharp gradients and with sigma X. Then we can actually start to look at, determine whether permeability is something we need to worry about or not. Okay, so, and that's a huge opportunity that we otherwise don't have a way to do.
By the way, we do have people online, and folks on online, if you have questions, you can type in, and maybe one of our fellow can read the questions. Anyway, before, any other questions? I saw some hands over there.
I did have a question, but he asked the question. I wanted to ask the significance of the B value. So, and you just answered it, but like, would it be fatal if we didn't know the V values in a diffusion MRI study? What would you say?
Certainly, that's a factor that as I hopefully show here, if you don't know the B value, you cannot disentangle the different effects what you're measuring. Yeah.
Thank you.
But what at my point, we need to know more than B value. Okay, we need to know the G, the little delta, big delta, rather than just the B value. Yeah.
Please.
So obviously very exciting talk, and I mean, Noddy as one of the models, rather than deciding which is the right model, right? Because there's many around, the tensor breaking down, obviously in difficult fiber crossing situations, and then Noddy having its strengths, and they are also being constrained with spherical deconvolution. So rather making it a thing about which is the right model, as opposed rather look at what is the most impactful application of a given model, right? So what would that be for Noddy, from what you see today in terms of the clinical utility of the method?
I think, yeah, so I think the jury is still out, I will say. I think a lot of reasonable success measured by publication has been done, but I think my personal feeling is, I think, Noddy, in the sense that was one model, which I think what we got it right is, I think we understand the importance of simplicity. Simplicity, we pay the price in terms of accuracy, but what we gain is precision. So I think Noddy, the first model, I think we try to strike the balance well, but still not enough, because the diffusion data is just far too noisy, which I didn't show you. Didn't run out of time, is to show you what the sort of effect of noise on Noddy parameter estimation is quite profound. And I think having a system where SNR is dramatically better, in a sense that what we can do with it is we can get significantly more precise Noddy measures. And that will directly impact the kind of clinical benefit. At the moment, well, one could say Noddy is not useful, but I'm certainly hoping that it's because we simply don't have the right data, and then the measurements are too noisy to detect the differences. We actually are there. So I think I'm certainly looking forward to trying out this technology on the CMX platform, and hopefully in 5 years' time, we'll have an answer, a better answer.
Any other questions? Dr. Liu, can you check if there's any questions online, please?
Yeah, we have one question from June webinar. Other than making reconstruction faster, how can AI make measurements more accurate with lower quality data? For example, lower gradient strength or lower p-value or lower number of directions?
Yes, that's a good question, I think, but also potentially controversial one, which I think the way I see AI is it's very much a database query exercise, for lack of a better word. And I think essentially it's a very intelligent, very flexible prior generator. So essentially, depends on what prior database you build, the kind of query you can get from it is as good as that. So that if you're looking at a very rare cases, and AI will struggle. But for more common cases, which I can certainly see AI can benefit, what we do, for example, I didn't have time to talk about a technology we developed called a Sandy model, which is one of the slide, where we can go back. I think there was little clue which I didn't mention. So yeah, so this slide, this is the NeuRite model where it come from. You see a little thing called SOMA not included. So in fact, we now propose a model to do that. So in gray matter modeling, we concern ourselves with the permeability of the membrane, but also ignoring the big SOMA in the middle of the dendrites, where the dendrite is projecting from. But to make the measurements, a technology we developed called Sandy, really in human system, we sort of get close is in the 400 millitesla connectome system. There are only 5 in this world. So one we are looking at in collaboration with my colleague in Fudan, which they have one of the connectome system. We are trying to use AI to learn how to synthesize the kind of measurements we can get only on the connectome scanner from a low field scanner. So at the moment we're trying to do it with a, say, Prisma. But I think with maybe Sigma X, perhaps we can get it closer. We can, if I try to learn the similar signal from Sigma X, we'll be have more realistic, more likely to get something sensible and do that. So that's, in theory, it's possible, but I just want to say it's I want to be cautious about what promise what we can or cannot do.
I also have one question about this whole AI thing. The students, if you, as you're now the center director and runs the center, and then if you look at the students who want to do the imaging, they are largely motivated by applying the AI technology in the medical imaging direction so that they can build their career on the topic, as it is such a hot topic right now. What do you suggest as a modeler and MR physicist?
So maybe, yeah, the good question. I'll just put on to the where I was having mentioned that. I think, I mean, the way I see AI is just a modern world of statistics. Okay, so for me, statistics is nothing but a tool, an essential tool we should all know. Therefore, everybody should know AI. We should know how to use it, when not to use it, how not to use it badly. So I think from Foster's perspective, I'm a complete advocate. I think every young person should master AI, knowing the strength and weakness equally well. But to use it, I feel that we need domain knowledge. And that's where, say, MR physics in our domain, or could be other domain, medicine. I think AI, in my view, simply not going to replace clinicians, even say some people are radiologists, but what they don't realize, radiologists are not just looking at the pictures. I think we have a leading radiologist here. Radiologists are trained clinicians. They understand the whole literature of the clinical science, and that information being combined with the interpretation of the image. That combination, that's what's happening. And AI itself, certainly we're not there yet to be able to use AI to be able to have all that together with interpreted images. So I think, in my view, the right approach is all young persons should understand master AI, but get into a particular field they're passionate about and apply AI in the right way, make a contribution in their field of choice.
Great. One last question that you want to ask? Okay. Without any more questions, please thank the speaker one more time. Thank you very much for this wonderful presentation.
All right. Our second speaker this morning is Professor Jung-Ho Lee. He's going to give a talk titled Towards Resolution Myelin Functional Imaging.
Anyway, welcome to Seoul National, and my name is Jung-Ho Lee, and I lead the lab in electrical and computer engineering department. And let me briefly show you. Okay, we're fine. Proceed. Okay, that's my lab. Yes, we do MRI, and we heavily invested in the AI, as that's the only one of the major motivation of my students joining the lab, as they have the opportunity of developing the cutting edge technology in AI, especially in the medical imaging, especially in the MRI field. Just a quick, aside from the major presentation of this myelin imaging, I just want to highlight one of the AI technologies that we develop in the lab. It is so-called, predicting before reconstruction. So my lab has this long history of developing these fast imaging technologies, and one of the the new direction that we find for the reconstruction is this new topic. So you probably have heard a lot about how we can make a new images from old images. For example, if you have a T1 weighted image that you just acquired from your scanner, you can use AI to transfer that to T2 weighted images or flare images. It will not be perfect, but if you just simply look at how the images are translated by some of the AI network, it does a pretty good job. You get a very similar looking images by having the data. Of course, you don't want to use it for the diagnosis, as it might lose the very important, valuable information by doing just conversion. Sometimes we do have this old data that we acquired like a year ago. If you are doing like multiple scans every year, then you do accumulate the previous data sets. And if you look at 1 year before your brain images of the same T1 contrast to the current, T1, contrast images, the two of them will look pretty much the same. Hopefully, if it is different, then you begin to worry about. And some of the rich people do it all the time. Somebody from the Facebook, the famous guy, seems to like it, and he scans his body like 4 times a year. And then, think about, head spending the whole body scan like every, 3 months. That's painful. And hopefully some new technology using AI can help him or help us so that we can have more frequent MRI. So our motivation is, okay, let's use all of these data sets, including your age, your clinical information, and also like any of the like scan intervals or whatever data is available for you. And then let's predict the image that you are acquiring at this moment. And then we can, again, we will do the scanning. We are not just, believing what AI will give you as the output, but let's do the scanning. But this time, let's do heavily undersampled data collection. And then we can combine the two in a way that we use a lot of information from these prior data sets that you predicted, and then truly acquired data of smaller number, fast imaging can be combined together to generate these reconstruction images. And at this point, yes, we tried it with a few options. The first option is predicting the flare images from either T1 or T2 weighted images. So if you are scanning MRI, then you go to the scanner, and then probably T1 may be the first images that you collect. Maybe after that you collect T2 and then flare. Then let's use this first, and second scan so that we can have a shorter scan for the flare, as we can predict a flare image from T1 weighted and T2 weighted images. Of course, I'm not saying that we will not collect any data for the flare. We still collect the data, but by using this prior information and doing the prediction from these images, we can heavily undersample our flare data collection. And maybe in the future, we can, adaptively collect the data that we need to compensate what was predicted to the final images. So that's the result, that we generate this predicted image from the T1 weighted and T2 weighted images. Yes, as you can see, it does a pretty good job by combining these two. Okay, I don't have much. Anyway, if you look at the third column, then you can see that the prediction is pretty good as compared to real acquired flare images. You can do the same thing for the longitudinal data sets. Like if you acquired the data 1 year ago, and then you give all the parameters that you want to have, and then try to extrapolate the current brain status of yours. Yes, again, prediction does a pretty good job, as the power of AI is here. And those information really help us to reduce the total scan time, as flare collection can be only 1/12 of the original data collection without acceleration. That's a really fast, or small amount of data sets. It's only 8% of the total data that are required to generate the original flare image. So first, these days, acceleration factor of 3 is common, or 4 is common. So our gain is, about 3 times, but still 3 times. And also, we do almost the same thing for the longitudinal T1 weighted image reconstruction by doing the prediction from the previous images like a year ago, and then collect only 1/12 or 1/8 of the data so that we can generate more reliable result by using this prediction technology. By the way, this is in collaboration with Professor Seung Choi in the Seoul National University Hospital, and I believe this is something that we use the AI in a right way, because we are not fully believing it, as Professor Gary Zhang just mentioned. You have to be careful about what it can do, what it cannot do, and I don't believe T1 to flare conversion can be perfect, even if you try all the data sets that we have in the world. On the other hand, if you use that information as our prior information for your reconstruction, while you are getting this sufficient amount of new data of the real flare scan, then we have a pretty good chance of combining the two, generating a reliable outcome of the result. Okay, that's a brief introduction of what I play with AI. And from now on, I will talk about this myelin imaging. Well, if you have any background of the brain, and then myelin is one of the interesting topic to be covered in the book. It's well known. Its well-known function is insulation. So my son once told me that and once asked me what I do for my research. I said I do the research on this myelin, and his response was, "Oh wow! So you're really working on this cable cable cover. Why not work on this like wires? Wires can be more exciting." And then I talked about Gary's work. But again, cable cover can be very interesting topic as well, as it not only does the insulation, but also does this saltatory conduction. And there are, this really, governs the structure of the brain as well as many of the functions, as it determines the, conduction velocity of the neurons, which is one of the important parameters there, I guess. And also developmentally, it's one of the interesting substance that it dramatically increases over the age of 0 to like 10, and it continues to increase up to 20 years old. And again, it reaches about maximum value at 50. So if you're around that age, you should be very happy about it. If you just passed it, that's okay. It gradually decreases, not drops dramatically. And there are like demyelinating disease like MS or NMO, so there are targets that we can work with. One thing that I will talk about is this brain plasticity. Some people, including myself, believe that myelin can be the like the substance of the brain plasticity, or key substance for the brain plasticity. So let's talk about that a little bit. And many people, if you're in MR, you know this in Short's paper that talks about juggling and how juggling training changes the brain. It's one of the shocking studies that I learned as a postdoc, and I was like, wow, we can do it. Like MR is so powerful that just learning juggling a few weeks and measuring before and after, you can see the changes in the brain. That's beautiful results. And people, like really excited about this result and continue to look at what are the substances that really changes them in the brain. And they use the mouse model, and they learned that myelin basic protein increases after the training. And also in this 2014 paper, they used genetically modified mouse that does not increase myelination at certain age. And then this new mouse does not know how to learn a new motor skill. So that means if there is no change in the myelination, there is no learning, at least motor learning, happening in the brain. So it seems that myelin is not just the consequence of the learning or neuroplasticity, but can be this essential substance that make this learning happening. So if we have a good biomarker that helps us to see this myelination change, it will be great, especially for the neuroplasticity studies. Another motivation of myelin study is this so-called myeloarchitecture. And I believe everyone here knows about cytoic architecture from Brodmann. Well, the bad news is cytoarchitecture is almost invisible in MRI, as cell density has almost no impact in MR signals. On the other hand, myeloarchitecture, which at least my point of view, as important as cytoarchitecture, is really visible using MRI. The challenge here is all about the resolution. You know, human cortex is usually like 2 millimeter to all the way to 4 millimeter wide. So if you want to have like 6 layers or more, you do need the resolution 2 millimeter, or let's say 3 millimeter. That's pretty thick cortex. And 6 layers, you need 0.5 millimeter resolution just to get the 6 layers there. And having the 0.5 millimeter isotropic voxel scans, any contrast, that's really painful with MRI. Like, for example, this is T1 map. So using MP2H from Max Planck Institution. They took almost an hour to get 0.5 millimeters isotropic voxels for this MP2H. Okay, highly motivated graduate students can volunteer for the study, not to move his head for the whole scan and get this, beautiful myeloarchitecture result. Not me. So let's try to find another way of, reasonably high resolution, hopefully 0.5 millimeters, and still get a nice contrast of myeloarchitecture. May help us a lot, as it is really the foundation of the neuroscience or modern neuroscience, looking at the different locations and being able to parcellate the brain into different sections. Another one, as I mentioned, 50 years seems to be the right year that you peak your myelination in the brain. And myelin seems to really, like any of the MR, myelin imaging can show this inverted, U-shape changes over time. So 50 years, just hit 50 today. not today, this year. It really marks my day. So I'm super excited about this ISMRM deadline that I submitted like 10 abstracts. Many of them will be my best abstracts ever. Anyway, MR, luckily, is really sensitive to myelination or myelin concentration. Like, for example, even the simple T1 weighted images, you can see the signatures of myelin everywhere. And the same is true for the T2. So people have used this T1 over T2 contrast, just weighted images, not the quantitative result, as a biomarker of the myelin in the cortex. I believe that's still very good, and that delivers you reasonable scan time. So it's one way of doing a good myelin imaging in the cortex. Another conventional and traditional way of acquiring the myelin is this myelin water imaging. There are multiple methods of it, and the challenge here is the SNR. Again, myelin water imaging, it requires multi-experiential feeding, which is sensitive to noise and all the things that results in the noisy outcomes, and your resolution is limited for like maybe 2 millimeter isotropic voxel size, which may not work for the myeloarchitecture. Another very good candidate is magnetization transfer imaging. Again, there are multiple options for this one, and many of the German groups are using this, especially the empty set type of contrast to get a high resolution myelin imaging. I believe that's one of the good direction to go. Hopefully I convince you today that there's a better way of doing this by using magnetic susceptibility imaging, and especially the technique that we developed in the lab called chi separation. There's a review paper that I brought just in case if you have broad interest in this area. Spend my time on writing reviews, so they will be helpful. Okay, if you are new to magnetic susceptibility imaging, this is like 1 or 2 slide introduction of it. So magnetic susceptibility is magnetic susceptibility is a property of a material. So any material like water, air, any of them has this physical value attached to it. Like for example, the reason why we can do fMRI is because of the magnetic susceptibility of deoxyhemoglobin is different from tissue. So that means this contrast is so powerful that it creates the whole field of fMRI. And also, in clinically, it is commonly used for this SWI, which is susceptibility weighted imaging, that helps us to find the hemorrhage or microbleeds. So already it's in the field of neuroimaging for like for science as well as for clinic. And what we found, or what a lot of people found, is in the brain we have roughly 2 or 3 major sources of magnetic susceptibility. The first one is of course myelin, as that's the topic of today's talk. And myelin has this negative magnetic susceptibility, which we call it as diamagnetic susceptibility source. The other 2 is in the form of deoxyhemoglobin, again, the fMRI source. It's paramagnetic susceptibility source that exists in the capillary and vein. And then there is one more thing called ferritin. And there are, of course, a lot of other things, but mainly these 3 things are sources of magnetic susceptibility in the brain. And ferritin is iron-containing protein. That's a nanosize, particles, but that they seems to, get together with neighboring ferritins so that they can have micron-size source affecting our, susceptibility imaging. Again, ferritin has a pretty large, susceptibility value, and it has the sign of positive susceptibility, so we call it as paramagnetic susceptibility source. So in MRI, if you have this space and the center voxel contains a magnetic susceptibility sources like this one, let's say we have positive source, then what it happens with the B0 field is it creates the field pattern, so-called dipole field pattern, around the sources. And this field pattern means that B0 field is no longer 3T. It becomes slightly more than 3T, if it is red color there, or it becomes slightly negative to the B0 field. And because of this perturbation, we get this extra signal decay called T2 star decay or R2 star decay, which can be divided to the R2 prime as well as R2. And R2 prime is really the source from this susceptibility induced signal decay. Another thing that happens is, if this is one voxel, if you see outside of the voxel, then it is not just the R2 star changes, R2 prime changes, but also the field itself is perturbed. But the perturbation is not limited within the voxel, but it goes outside of the voxel as shown here. So now with susceptibility sources in the middle, if you measure the field perturbation, we can measure it from outside of the voxel. So-called blooming artifact of the vessel comes from this source. So because we have this magnetic signal decay as well as phase evolution, we have 2 different ways of measuring the magnetic susceptibility. And also we are doing this quantitative mapping of these 2 measurements. We now call it as magnetic susceptibility mapping. And the natural 2 different images that we can measure is R2 prime map or R2 star map from the magnitude decay. And the other one is this field map, or more precisely, local field map that we can get from the phase of the MRI data. And the famous Professor Jablonski shows that this R2 prime is proportional to a constant and absolute value of the susceptibility. And another well-known relationship is this field map or local field is the dipole convolution of the susceptibility distribution. These two are really the governing equations for our work. So what does it says about especially the local field, which was new field of the research about 20 years ago in the name of the area of the quantitative susceptibility mapping. And this is really the simple picture that shows the primary susceptibility effects. And although there's a lot of other sources that contributes to the whole picture and makes the whole story complicated, but let's stay with the primary source. And you can see that if we have a susceptibility distribution in the brain, the result that we get as the local field distribution is the dipole convolution with the susceptibility distribution. That's a very simple and elegant relationship. It's dipole convolution. So as a scientist, you want to get the source image. You want to get this susceptibility map. And then what we have to do as an engineer is developing a deconvolution process. Okay, you measure the local field from MRI. All you need to do is doing the deconvolution of the dipole field so that you can generate this susceptibility map. And that idea was, spawned in 2008, 2009 by my friend Karen Schmele. Back then, we were at NIH with Jeff Dunn. And almost at the same time, it was done by Professor Yi Wang and in New York. So this new field of QSM really tells us that you can generate this susceptibility map, the total susceptibility map of each voxel by solving this inverse problem. Of course, the challenge is, this inverse problem almost always is not an easy problem to solve. It is ill-conditioned problem, so you need some idea how to solve it. And that race has been there for a long time. Anyway, if you solved it right, then we have these two maps now. The first one, R2 prime or R2 star map, and the other one is QSM map. The funny thing about these two maps is the fact that if we simplify everything and assume that there is only two sources, one is myelin as our negative susceptibility source, and the other one is iron or ferritin as the only positive susceptibility source, then these two maps begin to make a lot of sense, and also they are to a certain degree are very much complementary. Like if you look at this R2 prime map, if you have a large concentration of myelin, like for example the genu there, it gives you a high signal in R2 prime map. Well, the same is true for the iron. If you look at this deep gray matter, then they have a large concentration of this iron or ferritin. Then the value of R2 prime increases because of their concentration. Everything is almost the same in QSM, except the fact that QSM delivers the sign, meaning that if you have a negative susceptibility, it gives you a large negative sign in genu because it has a lot of myelin, and myelin is negative susceptibility or diamagnetic susceptibility source. On the other hand, if you look at this deep gray matter, again, it has ferritin, it has positive susceptibility source. Now the sign is preserved in the QSM. And if you carefully think about this one, well, of course, in the brain, by the way, it has a lot of mixture of the two. It has iron and myelin, and they can be combined. Deep gray matter, they can be combined even in the cortex, as Professor Fukunaka just demonstrated about 10 years ago, 10 or 15 years ago. And if you keep looking at these two pictures, then you get the feeling, okay, we can see the signs. We can have this absolute measurement or quantitative measurement. We have two measurements. We have two variables with huge, assumptions of simplification. Then now we can separate the two sources, even if they exist in the single voxel. So this is the whole picture of chi separation that we propose for myelin imaging. Let's say we have this positive susceptibility source, and we measure the frequency as well as the R2 prime. And we do the same for this negative susceptibility source voxel. And then you will see that the frequency shift is exactly the opposite, but R2 prime wise, they are the same decays that you measure. And if you consider a voxel that contains both of them, then story is very elegant in a sense that the field cancels out, so there will be zero value, whereas the R2 prime becomes double the original one, double the one of the two. So the two famous equation there is now modified to this one so that we can have the chi positive and chi negative that can be separated into different maps by using chi separation algorithm. And before I go further, again, I have to emphasize all this modeling work is based on a lot of assumptions, and none of them is perfect. It's just hopefully we want them to be the primary equation that give us a reasonable outcomes. But if you look at, how things really work, it's the assumptions of this chi separation. The first assumption is there is only two sources, which of course is not true, as we already ignored deoxyhemoglobin, right? Which is the whole fMRI people will not be happy about this. And also, it's whole based on the idea of Jablonski's static dephasing regime. But as Gary mentioned, we have diffusion in the brain, and that's all the diffusion people are working on for their career. And my lab ignores it. So it's really bad setting that we ignore fMRI people, we ignore diffusion people, and say that here's the new model that we developed. Luckily, so far, the result seems to be reasonably okay, meaning that our accuracy may be 50%, more or less. I don't know, that's a ballpark number. Anyway, with these strong assumptions, we were able to generate or separate the two concentration of the susceptibility. And acquisition-wise, this is the whole chi separation pipeline. First, we acquire multi-echo GRE so that we can generate this R2 star as well as frequency shift. We also need to acquire, this multi-echo spin echo, which is really painful and slow acquisition, so that we can have this R2 map. And from this R2 star and R2, we have this R2 prime that directly measures the susceptibility concentration. And from the frequency shift and R2 prime, we have this new algorithm that generates the positive susceptibility map and negative susceptibility map. With the magic wand of AI, as no one really acquires the R2 map, so we replaced it with the CNN so that R2 star can magically produce R2 prime with large enough data sets to train it. It does pretty okay job of doing it. And this makes the whole scan time to be 5 minutes for 1 millimeter voxel size. Otherwise, it's really challenging. Again, we come back to the idea of validation. We developed a phantom that contains two different susceptibility sources. So if you look at this construction, the first row has different concentration of positive susceptibility source. Second one shows the negative susceptibility sources. The third one is the mixture of the two. And we put it into the MRI and acquire the data. You can see that, yes, there is a pattern of the local field, another pattern of the local field, because they have the opposite susceptibility sources. The pattern is the opposite. Here you see that up and down shows the positive. Here the left and right shows the positive frequency shifts. So saying that, okay, they do have these opposite susceptibilities, making a different patterns in the local field. And if you look at this third row, then the two sources canceled out, giving us zero frequency shift. That's beautiful, right? just like the expectation that we had from our theory. On the other hand, if you look at this R2 prime map, yes, there is an increasing R2 prime as we increase the concentration of the sources. And here, the same is true for the negative susceptibility source. Again, the mixture of them adds up so that they can have this increased R2 prime result here. With chi separation, yes, you can separate the two outcomes, beautifully showing the positive ones here, negative ones only in the second and third row. So again, simplified world of the phantom, the method worked perfectly, and it gives you the quantitative outcome of the susceptibility measurement of each sources. We went further for the validation using ex vivo brain sample. This is the primary visual cortex where laminar structure is well known to have this line of Ginari, so-called Ginari line, which is the layer 4 of the primary visual cortex that has dense myelination as well as iron deposition, thanks to Professor Masaki Fukunaka's work in PNAS 2010. Because of this well-known, microstructure, we were able to validate our technique, as shown here. This positive map and negative map, they show this signature of line of Ginari in layer 4, and the same is true this myelin map. And one thing that is shocking to me is if you look at this cortex. Okay, that's really hard. Okay, that's the surface of that's the surface of the cortex. And if you go, okay, that's hard. Too short. Anyway, if you go tangentially toward the white matter, then you can see how the myelin changes and iron changes. And the two patterns are different in a sense that deeper layer of the cortex, myelin is relatively low in their concentration, whereas iron seems to be higher in their concentration. You can compare the chi positive and chi negative and just go from the surface of the cortex, tangentially to the white matter. You can see how the profile changes. And then you will see that positive and negative has this different profile. Anyway, we did some of these correlation studies. We picked a few RIs, and then the myelin map and the myelin stain from the loxo-fast flu, again, which is not quantitative map, but okay, you can show some correlation between the two, and correlation R square is about 0.77, which is pretty high number. Well, you can, again, this is what I did for negative map, that you can show the cortical profile of the myelin as well as myelin stain, showing that, yes, they do have pretty good correlation between the two. Well, we are not the only lab who validate this technique. This is Shanghai Zhaoteng group developing their own algorithm that showing the same phantom as well as showing the, this is, I believe, one of the monkey result with the stain showing the correlation between this susceptibility separation technique as well as myelin contrast. So if we go to the applications looking at this in vivo result, yes, the myelin map or chi-negative map seems to show a pretty good correspondence to, this is the column that you are looking at. And if you look at this deep gray matter areas, then the beautiful this myelination structure of the internal caption really pops up in the images. And that's the same for this positive susceptibility map, where you want to, the far right column, where you have this pervina within thalamus that has high concentration of iron, and that is well depicted in this positive and negative susceptibility maps. One thing that I really like about this technique is this particular example of a MS lesion. In MS lesion, especially the one here, the flare images will show hyperintensity in MS. That's typical case of the MS lesion. And the positive, and the QSM, which is the combination of positive and negative susceptibility sources, didn't detect this change of flare, high hyperintensity lesion. That was because they have lost iron deposition as well as myelin at the same time. So normal tissue has this amount of positive susceptibility and negative susceptibility. And if the disease made them to lose this iron as myelin, then QSM will not show any changes, whereas the chi separation result will show the changes. So immediately the technique becomes a better biomarker for MS lesion studies. And there are multiple studies published in this line of the research. I'll skip this slide by simply saying that again, AI with its magic first have limitations. They do save our scan time to a certain degree that we produce reasonably good results. And we further validated that we can do a similar outcomes by using the AI-based reconstruction of this chi separation. That lesion appearances in MS seems to be the same, whether you use the classical reconstruction approach of long scan time versus AI-powered reconstruction with a short scan time. At least the lesions are different only in 1% of all the MS lesions that we studied, which was 500 lesions. Another one that we got super excited about is cortical profiling, this laminar structures that we want to see, or myeloarchitectures that we want to see. We were able to show, if you look at the far right image, the blue curve is the myelination change from the 50% of the cortex all the way to 200% inside of the white matter. And then we can see the myelination gradually increases toward the white matter. On the other hand, the iron deposition seems to peak at the boundary of the gray and white matter, as shown in this plot. And also that is confirmed by this Kirillina study in 2020, that the iron deposition really peaks at the boundary of the gray and white matter, whereas myelin has different profiles as compared to iron. And chi separation seems to catch those characteristics well enough. Well, 7T is there, and one of the power of the this susceptibility imaging is the fact that higher field helps, as the magnetic susceptibility effect increases linearly with the field. So that's a good sign, as the proton density as well as the SNR, overall SNR, increases linearly with field. That means we have like roughly P0 square benefits of doing the high field MRI for magnetic susceptibility contrast. So this is, by the way, this is the templates that we generated with the 3 Tesla. And this is really the 7 Tesla images that you can see of details of the images. Of course, if you look at it, the first obvious thing is all these veins creating a high signal because there's a large deoxyhemoglobin concentration. So that biases whole visual assessment of the images. So now the lab is developing how we can remove these vessels by using MR physics. So very excited about upcoming results. Again, the high resolution scan of like sub-millimeter voxel size will give you a detailed images of the like brainstem. That's another very exciting outcome to go. And also, like, you can go further to 11.7 if you are doing the animal imaging. This is the rodent imaging in collaboration with Dr. Lehercy in Paris. You can see beautiful myelin, chi negative images that corresponds to the histology from the literature. a lot of applications in MS makes a lot of sense. I'll just move on to save time. Some of them is from our group in collaboration with clinical people, and some of them is from other groups that they used our toolbox to do their research. This is another research looking at this small vessel disease, a special subset of small vessel disease called CADICEL. And in this particular study, Dr. Ewers has demonstrated that myelin is associated with slower processing speed in their patient measurement. And he was really, really careful in analyzing the data. So they had all these diffusion measurements and they control for the diffusion outcomes. Still, kind negative shows that there is a association with the processing speed of the brain. So that really gave me some direction to go to the neuroscience with this new technology. Well, people now looking at a lot of different things. One of the things that I was really happy about this is developing brain, where they are scanning this, the newborns, like 43 weeks. It's really newborn baby. And at that age, you don't have much myelin, you don't have much iron, so there's nothing much to see. So individual subject-wise, that's the first, role where it looks like a garbage. So when I first saw the images, okay, my first response was, okay, you cannot do it. It's just, too noisy. I don't see any structures and how to do the research. And then he was very, persistent and then generate this averaged images, a lot of babies. And that averaging really removes all this noise and then kept the structures. And he was able to show some of the features of these negative susceptibility and positive susceptibility maps that begin to make sense structurally. And now he's doing these longitudinal studies so that he can see the brain developments. Again, another emphasis on the limitation because modeling never is perfect. We hope that this is really the one that we deliver is the primary effect, not the secondary or thirdly effects. With the static dephasing regime that roughly ignores the diffusion, and we assume that two sources and isotropic susceptibility, then we can generate these images. Vessels, it's a huge complication, especially if you look at the surface of the brain, where you want to look at these cortical profiles. Vessel is everywhere in the surface. That complicates our results. So now we are working on those topics to remove them so that we can generate this more reliable myelin maps. So this will be almost my last slide. Again, I'm not claiming that chi separation negative map equals to the myelin. But at least what I can say is, it can be one of the good surrogate biomarker of the myelin. And AI will be never perfect, but at least, give you some confidence of how you can do it in a reasonable scan time. As MR, from my perspective, that's what really matters. 5 minutes of scan time. Patient can be scanned with the technology so that we can get a lot of clinical information, help them to see new things in the future. High field is something that I got so excited these days, and nowadays people have 11.7T for the human. It's available in Paris, and hopefully they become available in Korea as well. So there's 11.7 projects in Korea that's ongoing. And their recent result is, can get this 0.2 by 0.2 by 1 millimeter voxel size in 5 minutes of scan time. That's beautiful susceptibility mapping or susceptibility weighted images from 11.7. We have this toolbox available for everyone, and we do support the research. And hopefully we can have all these other sources applicable for the future, not just the negative map, but positive map as well. So this is my conclusion. Myelin is more than cable wire covering. So it's an exciting topic that I'm spending almost my whole career on the topic. And our new method of chi separation, we believe it's a worth it tool that hopefully in the future it becomes noddy. It makes the noddy impact in our neuroimaging community. And I believe it's really about the application. You need to find one good application that clinicians are using it for their routine scans. So that's one of the direction in the lab to go. With that, I really want to thank my students who did all these works. So my lab roughly works this way. I kind of say, okay, this is really exciting topic. Do you have interest in it? And if the person gets his interest, that's the research direction that we go. And really want to thank them for their contribution to this exciting topic of the research. And also, I want to thank you for coming to this, symposium, and thank you for listening to my talk.
Thank you, Professor Jung Lee, for the great talk.
Yes, really great talks, as usual. I'll start with the part of the machine learning, the beginning. So have you thought about which part of the case space you shall sample? I'm sure you.
Yeah, that's the right now. It's really the beginning of the whole research. So we do just undersampling with the distribution that we believe, based on some of the distributions that we believe it is important. So we are not equally sampling 1/12 of the case space. We do some estimations and try to get the lines that we believe it is important. So it's a, like PDF based, sampling. But this sampling pattern is now fixed for everyone. What I believe as a future is, like we begin to acquire the case space and say how accurate, based on maybe it can be a single case space line or multiple of them. And then we say how accurate our current prior is. And if it is not accurate, we acquire more. And then with these new data sets, we can upgrade our outcome combined with the prior. And then maybe at one point, some of the data will tell us that the accuracy reached high confidence, then you no longer require to acquire more data. Then we may stop the whole scan. But this one, as an MR physicist point of view, is more like a dream that you acquire data and on real time you tell us whether that's good enough. And you need some criteria how to tell these lines are good enough estimates of the 99% accuracy of the outcome. So a lot of things are under development. We did develop the real time way of collecting the data and estimated some of the accuracy in previous works, not because of this idea, but because of other ideas to do it. So maybe we can combine some of those ideas so that we can really deliver one technology that shortens the total scan time, not based on fixed sampling, but based on that person's changes of the brain.
Thank you.
So thank you very much for your beautiful presentations. So I just want to know about your chi-separation. So I think it's upright to the gray matter. It's way difficult compared to white matters. So I just wondering. So what is the most challenging part when you apply the chi-separation in the gray matters?
So pain is really, really pain. Like brain, like if you look at the surface of the brain, veins are everywhere, and then they have surface veins that are pretty large, so it creates the field at least 1 millimeter or even 2 millimeters that like kind of give you the influence of perturbation within the cortex that biases everything. So that's why 50% of our cortical measurement for the cortical profile study was removed because I cannot believe any of them. So that literally removes like one voxel. So it shows a huge problem. Now we are developing a technique that, roughly speaking, large veins and their effect can be mitigated. We cannot remove it, but roughly mitigate it by modeling it. So hopefully that technology helps us to do something. The other thing is, superficial cortex doesn't really have much myelination nor iron. So there's nothing much to see to begin with, or nothing much to give us enough contrast to noise ratio. So maybe we can just ignore them. But again, those are the key challenges, that our contrast is based on how much myelination you have at that location, or how much iron deposition you have at that location. If those two are not there, then contrast tells you zero susceptibility, and yep. So luckily we are looking at these water protons, not just susceptibility itself, as susceptibility influences water proton phase changes. So we are not directly looking at the susceptibility. So this makes it different from myelin water imaging, where they are directly looking at the myelin water protons. And if that number decreases, their SNR decreases. Whereas here, water is everywhere, and we are looking at the phase. So SNR still is preserved even if you don't have concentration of iron. Yes, please.
Oh, yeah, here we go. Yeah, so I'm just wondering, for the AI-based kind of reconstruction with the undersampling, I mean, to what extent is there a risk that a very subtle effect that might be relevant clinically would not be detected, because you're basically just going to assume that it's going to look like the average of the, you know, the sample that you've trained the AI on?
That's a perfect question, you know, and you know that's the job that I will do with Seung Choi in near future. And you know, actually, his right, his first response is we have to look at all the subjects and show the relevance of this, you know, technology to the clinical evaluation, so that we can report that the lesion appearances as well as small lesions detectability changes or preserved based on technology. You know, maybe in the future we know that there is a hint of changes in the small lesions, then we can occur the edge of K-space more efficiently, or more as compared to central portion of it, as there are the information and there are some correlation between the resolution as well as this lesion size. So maybe we can target those areas for the data collection. But again, all the, you know, this is really something that we've worked on last, you know, I don't know, like 6 months, and get the paper, you know, on the archive. So a lot of questions are there, a lot of validation needs to be done, and very exciting time to do this research. Thank you.
Do we have any questions online?
There's two questions from Ho-Jun Lee. And first one is, are there any benefit of high performance gradient for chi separation?
The answer was no at the very beginning. So there was like, we have this amazing machine and we're not using it that well. And luckily, I think there is now, because of this flow compensation, we are using flow-induced, you know, image shift as a source for the compensation, and that one, you know, higher gradient seems to help us.
Yeah. And the second question is, can there be any benefit for modeling microstructure, considering information gathered from diffusion and susceptibility?
Yes. That's why, you know, Gary is here, that we will collaborate on the topic so that we can combine it, so that we can get a full information out of these, you know, technologies. We'll be excited to see how it spans over the next 2 days, or today and tomorrow.
All right. Any other questions? I just have a quick question. So if a researcher, let's say a stroke researcher, wants to validate his intervention, how does myelin imaging play a role?
Can you say that again? Validating
the intervention that he develops, like
okay.
and then he wants to use myelin imaging, and how does it tell? Like, how does it come into play?
Well, so again, our technology is always the indirect biomarker of myelin. So if you're really doing the validation, histology is the way to go. And histology is never, perfect because of a lot of limitation, and it is usually not quantitative. So you really have to go this micro, what is it? The TEM type of imaging, so that you can really quantify everything and make it sense out of it. All of these steps seems to be very, very challenging to do it. So, as a step back, as at least it is indirect biomarker of this. So if you're going for neuroimaging studies, try to show the effect of myelin to certain, intervention or some of the, like whatever, like study topic is. This can be again used as an indirect biomarker. And the power is not so much about the accuracy. As we sacrifice the, like some of them because of the limitations of model, but really about the applicability. Like again, 5 minutes of scan time, you can get these informations, and then you can generate a lot of assumptions, well, hypotheses about your study, and show whether this biomarker can be used for your future studies and whether this biophysics makes sense to you. And as long as you understand the limitations and you understand the principles of it, there are pretty good chances that these outcomes make sense. And if it is valuable, there are more people who will do more diligent, validation of the result. So I think really not just the single paper's work, it's more like a lot of people contributing together so that they can use it for the future.
Thanks so much. Okay, that's it for the morning session. We're gonna reconvene after lunch. Thank you so much.
Thank you.
Okay, let's go ahead and begin our afternoon session. Okay, our first speaker is Professor Seung-Hong Choi. He's going to give a talk titled Exploring Lymphatic Flow, Innovative MRI-Based Visualization Approaches.
Thank you for introduction. Today I will talk about relatively new concept in the brain, lymphatic system. Basically, I'm a neuroradiologist, mainly working in Seoul National University Hospital, but half of my works are about research, and my research focus is that I want to use cutting-edge MR technology in patients and some volunteers to evaluate the biological phenomenon using MRI. So truly happy to be a member of SNUBIC. I want to say SNUBIC, the SNUBIC Brain Imaging Center. I have enjoyed a collaboration with the MR scientists and some other relevant MR field researchers. Today, as I mentioned earlier, I want to talk about new concept, lymphatic flow. I will cover some brief introduction of lymphatic pathway, and I want to say the why we use MRI for lymphatic flow, and I will leave you some brain diseases and how these diseases are related to lymphatic flow, and if there are some problems lymphatic flow in neurological disease patients, how can we do to improve lymphatic flow? That is kind of solution in our the healthy status. Okay, let me start with lymphatic pathway and MR imaging application. When I was in university student, I was almost 25 years ago. In biological textbooks and medical textbooks, there was a simple description regarding CSF, cerebral spinal fluid. It covers brain, and mechanically it protects brain. That is a main function of CSF. Very simple. And there was another very strict description. There was CSF never enters brain parenchyma. So, but this knowledge totally changed over last 1.5 decades. Currently, we think that obviously CSF enters brain parenchyma and it has great function to clear remained waste in the brain parenchyma. So we say that lymphatic flow is kind of CSF flow from CSF space to brain and outflow of brain parenchyma through meningeal lymphatics. And finally, meningeal lymphatics are connected to the neck lymphatics and return to lymphatic main flow. Until now, we believe that lymphatic flow starts from CSF space and it enters to brain parenchyma through major CSF channel, that is aquaporin 4. And then it has function to clear waste in the brain parenchyma and flow into perivenous space. It's kind of perivascular space. There is still some debate regarding which one is inflow and which one is outflow, or they can be mixed. So, but major population, I believe that it didn't touch anything, but it moved next. Anyway, the arterial perivascular space is kind of a major entrance, and the venous perivascular space is major, the outflow tract. In 2013, there was interesting paper regarding aquaporin 4 channel in Science Translational Medicine. In this study, the authors used knockout mice for aquaporin 4 evaluation, and they compared lymphatic flow in both the groups. One is normal mice, and the other one is aquaporin 4 knockout mice. They traced the lymphatic flow using fluorescence imaging, and they finally observed that in mice with aquaporin 4 knockout showed late the flow of lymphatics. So after this study, there have been several similar trials to show which this report is true or not. Many researchers show that it is true. So currently, we totally believe that aquaporin 4 channel is quite important entrance of CSF to brain parenchyma. And there are several methods to evaluate lymphatic flow by imaging. And a simple way is to use the histopathology after injection of kind of dyes, and then we sacrifice mice or other animals, and we can evaluate the how much tracers enter brain parenchyma through lymphatic flow. And the other one method is the 2-photon microscopy. In this, the skull window to trace the radio or fluorescent tracers. And one more method is that transcranial microscopy imaging. Then these three methods can available in human in vivo imaging. So we need the new modality to see lymphatic flow in human system in vivo. that is MRI. I want to share some MR imaging modalities to see lymphatic flow. The one of simplest method is TTI ALPS. That is based on TTI mechanism, and in this idea was invented by Taoka, Professor Taoka in Nagoya University, one of my close friends. His idea is very simple. Actually, lymphatic flow is along with the vascular structures. So if we measure diffusivity along perivascular space, we can guess how fast lymphatic flow is. So in these methods, we measure relative diffusivity along X, Y, Z axes. As I mentioned earlier, lymphatic inflow and outflow along with perivascular spaces, the periarterial or perivenous. So if there is problem in lymphatic system in any way, there must be some enlargement of perivascular space. So if we observe the enlarged perivascular space, it must be a result of the lymphatic flow disturbance. So there are several studies using these methods, and they reported that the dementia patients have the enlarged perivascular spaces. And there is the invasive methods to measure lymphatic flow, that is intrathecal contrast agent injection, MRI. And the MR contrast agent is based on gadolinium, and gadolinium makes the T1 shortening. So after injection of gadolinium, the T1 shortening makes high signal intensity on T1 weighted imaging. You can see high signal intensity after injection, 1 hour, 3 hour, 4.5 hour, and 24 hours after intrathecal injection of gadolinium agents. Intrathecal means intra-CSF injection at lumbar area. You can see the movies or dramas. There are some very sick patients, and they aspirate CSF at the area of our lumbar region. And it's a quite similar procedure. And after injection of gadolinium agents at the lumbar level, and it flows with CSF and gadolinium agents enter brain parenchyma. It makes high signal intensity in brain parenchyma. We trace this signal intensity change. We can guess how fast lymphatic flow within brain parenchyma. And in this study, the authors found that NPH means normal pressure hydrocephalus, enlargement of ventricle. It is mainly because of disturbance of CSF flow. So in NPH patients showed a delayed lymphatic flow. But unfortunately, intrathecal injection of gadolinium agents is illegal in many countries like Korea and US and Japan. A few countries allows these methods, like Germany or China. These countries prefer the challenging methods if these new procedures can be helpful for future the human health. And there is a safer way to measure lymphatic flow after intravenous injection of gadolinium agents. This method is not directly the measurement method. Actually, after intravenous injection of gadolinium, gadolinium agents, the flow along with the blood vessels, and then it enters to CSF space through choroid plexus. Because choroid plexus is a major organ to make the CSF, and choroid plexus is kind of a filter from blood to CSF. So when the blood is filtered by choroid plexus, some gadolinium agents can enter CSF space, and it flows together with CSF. And finally, gadolinium enters brain parenchyma. So we can measure T1 signal intensity change after the intravenous injection of gadolinium agents within brain parenchyma, and we can calculate the lymphatic flow. So this idea was introduced by Tauka as well, 2018. And in this study, the authors injected gadolinium agents intravenously and measure brain parenchymal T1 signal intensity change. You can see increase T1 signal intensity and decrease T1 signal intensity as time goes by. And we used these methods to measure human lymphatic flow. In volunteers, we injected gadolinium agents. It's totally legal. So, and we measured T1 signal intensity change within brain parenchyma, and we can calculate the lymphatic flow by this way. I will share some research results with using this method. Okay, let's move on to next topic, lymphatic system and brain diseases. Basically, dementia, we think that there must be increase in pathological proteins like amyloid beta and tau protein and the alpha-synuclein in Alzheimer and Parkinson's disease, respectively. That is obvious. Pathological protein overproduction is the main cause of these dementia pathologies. However, we believe that there is one more pathological process, that is problems in clearing these pathological proteins. As I mentioned earlier, the lymphatic flow is responsible for this clearance. If the lymphatic flow decreased pathologically, that makes the more aggregation of these pathological proteins within parenchyma, it makes disease status more severe. So another, the mechanism of dementia pathology. So there have been several studies to show lymphatic flow make these neurological diseases. Our group wanted to see these results are replicable or not. So we used our ADNI data set and we measured lymphatic flow imaging markers like TTI-ELPS, the bold CSF coupling, and fractional anisotropy and mean diffusivity to compare the normal and MCI and Alzheimer's disease groups. Interestingly, we found the similar results to previous studies. There was decrease in the TTR-ELPS and bold CSF decoupling in the MCI and Alzheimer's disease patients, and we found significant changes in FA and mean diffusivity values as well. And one more interesting thing is that these the clean party flow measurements based on MRI are correlated to each other. That is one more interesting finding in our group. And I want to show several interesting changes related to the other conditions like aging and alcohol and something. And this study showed that according to aging, there is change the clean party flow. In old animal shows a decrease in clean party flow. It is mainly because of decreased aquaporin channel amount and quality. And according to this study, it's very obvious that aging can make some decrease in clean party flow function dysfunction. And there are some patients with TBI, traumatic brain injury. TBI is just alteration of BBB. Many previous studies reported that the relationship between the TBI and BBB disruption. But one more, the significant change after TBI is clean party dysfunction, resulting from the aquaporin flow decrease. And we passed through a severe COVID-19 period. There have been several studies regarding COVID-19 and brain pathology and the systemic pathologies. One interesting thing is that clean party pathology. Actually, COVID-19 virus directly attack CNS because they measure the entrance protein is ACE2 receptor, and COVID-19 virus attached to the ACE2 receptor and then enter brain parenchyma directly. And because of that, we know that several CNS pathologies related to COVID-19. One of them is anosmia, no smell. We cannot smell after COVID-19 infection because direct infection of COVID-19 to olfactory nerves. So we met some patients with COVID-19 in our hospital. You can see high signal intensity changes along the olfactory bulbs. That function is smelling. After COVID-19 infection around the nasal cavity, it disrupts nasal lymphatics as well. So one of the outflow tract of clean party flow is around nasal cavity. So the COVID-19 syndrome remains some severe fatigue after injection, even the physical recovery. Some researchers mentioned that it is related to the clean party dysfunction after COVID-19. The major mechanism is that COVID-19 disrupt clean party flow. And this study is quite interesting to me because I think that many of audience enjoy alcohol, beer or makgeolli or wines. And I found this study and I laughed a lot. And I wanted to see the alcohol effect on clean party flow. And there is already a study. And this study, the authors tested low, medium, and high dose of alcohols in mice. And they found that low dose alcohol can enhance clean party flow. It means that it can be helpful to protect the neurological diseases like dementia, because as I mentioned earlier, the clearance of waste within brain is quite important to prevent dementia, and alcohol could work for that purpose. But this study was not done in humans, so we have to wait until there will be the human study. Okay, glymphatic flow is critical in brain health. So what can we do to prevent glymphatic flow, the disturbance, and how to protect our brain health? The one of method is to artificially increase glymphatic flow or maintain glymphatic flow. And this study was reported about 12 years ago in Science, and the authors claim that sleep is very important in glymphatic flow, and they used the two-photon laser scanning to measure glymphatic flow, and they compared glymphatic flow between sleeping and awake group. And the message is very simple. Sleeping highly enhances lymphatic flow. And one more thing is that the anesthesia also has make similar effect. Anyway, sleeping well is very important to enhance lymphatic flow. And the other one message is that if you sleep well, your brain can be healthy. And so in our group, we wanted to confirm this phenomenon in human. So we recruited volunteers of 25, and we measured lymphatic flow by using MR scanning twice in one volunteer, and during daytime and during nighttime. For a daytime session, after baseline 2-hour scanning, they had normal activity, and then we rescan 12 hours. And in nighttime scan, after 2 hours baseline scanning, they should have sleep well, and we rescan the 12 hours later. And for this study, Jong Lee, a friend of mine, the first speaker of today's conference, developed the very the reliable T1 mapping methods, and to trace T1 value changes within brain parenchyma. And after MR scanning, we segmented brain areas, and then we measure T1 changes. And we injected gadolinium intravenously, and we measured T1 changes within each brain area. And you could see decrease in T1 values, and then a recovery of T1 value as time goes by. So you can see difference, the slope during a recovery period. So this steeper slope means a faster lymphatic flow. So in this study, we observed during sleeping, the lymphatic flow faster than daytime. It was not that dramatic comparing to animal study. In human study, slightly higher flow was observed during nighttime. I think it's the sleeping effect is very accumulative. The long time sleep deprivation can be problematic in human system. And there is another interesting study that is about anesthesia and Green Party. In previous animal study, ketamine and joylanin is kind of the strong anesthesia methods can impact the increase Green Party flow, but the gas anesthesia such as isoflurane have bad impact to Green Party flow. So we have to consider when we use sleeping medication, the methods, what kind of drugs are used for sleeping. And okay, and the other interest to Green Party flow is that exercise. We know that exercise is generally helpful to the health. So many kinds of research, the long-term exercise can improve your health and cardiovascular function and brain function. These studies are usually observational results, and this study is also same. And this study is quite interesting. There are two mice. One is exercising a lot, and the other one is resting. The authors changed blood these two mice, and the mice with last after donation of the exercising mouse blood, it shows the exercise effect even in mice with lasting. It's quite interesting. It means that in blood after exercise, there are several factors that it can have your health. Anyway, so exercise can improve your health. So I wonder if the exercise has a positive effect in brain. So I designed exercise program in volunteers. One is the single day exercise, and the other one is a long-term exercise during 13 weeks. We compared the Green Party flow before and after exercise. The two ways, one is single plus, and the other one is long-term exercise. The result was interesting. We observed that long-term exercise makes increase in Green Party flow, but a single exercise does not have similar effect. So if you do exercise for your health and brain health, you must exercise at least 12 weeks, long time. And for this study, we use one innovative methods, the inversion recovery Aladdin, that is based on ASL. We do not, for these methods, the gadolinium agents is not necessary. Just we can measure the slow-moving water molecule using these methods, and we optimize to measure very slowly flowing Green Party flow. And using this method, we also found the meningeal Green Party flow also enhanced after long-term exercise. Okay, and next step, we wanted to explain what kind of factors are related to this changing. And the results were very simple. After long-term exercise, Green Party flow can be enhanced. But we wanted to check there are some factors, the biological factors related to Green Party flow. So for this study, we sampled blood 2 times, before and after exercise, and we analyzed proteins within blood before and after exercise. And we found several proteins which showed the significant changes before and after exercise. And these factors are interestingly related to neuroinflammations. Actually, long-term exercise changes our inflammatory factors, especially related to brain inflammation. And these two methods, sleeping well and exercise regularly, are quite important methods to prevent your brain health. And one more question is that not sleeping well, not exercise regularly, what is other methods to prevent brain pathology? Is there any methods artificially to enhance clean body flow? So our team thinks that ultrasound can be kind of alternate methods if we do not sleep well or the exercise regularly. And in previous studies, live low intensity focused ultrasound can enhance the BBB disruption very surely. So the many researchers try to use live to enhance the brain, the flows through BBB temporal opening. In this study, we used live to enhance meningeal lymphatic flows. We just focused the ultrasound along with meningeal lymphatics that is very close to sinuses. Sinuses are kind of venous structures within skull and is quite near to skull structures. And we tested live in mice model, and we compared the control and the live application models, and we measured lymphatic flow after intrathecal injection of gadolinium agents. Intrathecal injection is illegal in human, but in animal is feasible. So it's quite very clear methods to measure the lymphatic flow in animals. And anyway, after the live application, we can observe the faster lymphatic flow. And we also calculated infusion rate, that is how fast gadolinium agents enter brain parenchyma after intrathecal injection of gadolinium agents. We also observed the faster infusion rate in mice with live. And our basic concept was proved in mice study, and these days we scaled up this device for human and monkey. And this study is from a monkey study using live device. We also observed similar results in monkeys. Okay, that is my final slide. It's obvious that the lymphatic system has relationship with several neurological diseases like dementia and other diseases. And regular exercise and sleeping well, they can help your brain health by improving lymphatic flow. And there can be alternate methods artificially to improve lymphatic flow, like live. And I heard that there are other the researchers stimulated the lymphatics, which results in improving lymphatic flow. Anyway, we will meet, I think, the other ways to improve lymphatic flow artificially. I especially thank to my lab members and co-workers. Thank you for your attention.
Thank you, Professor Choi, for the great talk. We're open for questions. Anybody has any questions?
I thank you for the talk. I don't know if this is true. I just saw it from somewhere. I heard that if you have sleep deprivation, then it's similar to having alcohol in your bloodstream. And while listening to your talk, you talked about how little alcohol can clear the lymphatic flow. And also, if you have enough sleep, it helps your lymphatic flow. So I wonder if what you think about this true or not true story about sleep deprivation.
Actually, very good question. We have a similar history of alcohol effect to cardiovascular system, and that is small amount of alcohol consumption, daily consumption makes some good effect to heart. So 1 glass or less than 2 glasses of wine can be helpful for the heart, the protection. We say that Jacob effect. The alcohol has Jacob effect to heart, not other organs. So small amount, decrease the cardiac problems, and more than the 2 glasses make troubles for the heart disease. It's kind of a similar idea. This is not confirmed in human bodies, just the mice study. And so the small amount I calculated in human scale, just 1 glass, the about 200 to 300 milliliter of the beer can be helpful only for lymphatic flow. They did not see other effects like the obesity or diabetes, the other cholesterol, other effect, nothing. Only lymphatic flow. That can be helpful. I'm not sure. So in my future study, I want to check this alcohol effect to lymphatic is true or not. I want to check. Yeah.
I see. Thank you.
Do we have any questions online? No.
I have one, if I may. Yeah, super interesting talk, and obviously a big topic at the moment with lymphatic imaging. In terms of timescales of the lymphatic vessels, the meningeal and the interstitial space, do you see a big difference in terms of the velocity of flow? And have you tried now with the CMRX, obviously higher gradient powers, to try to encode directly the flow that is occurring?
Actually, very important question. The flow scale is here. I cannot remember exactly how fast the lymphatic flow is. It's a few centimeter per second. The scale was that, and actually, we measured both ways to measure lymphatic flow. The one is intra brain parenchymal lymphatic flow using gadolinium agents, and the other one methods to measure the meningeal lymphatic flow using Aladdin and the IL Aladdin based on ASL techniques. Interesting is that they showed a very weak correlation between the two parameters. We thought that why this discrepancy was observed, we I think that the meningeal lymphatics are from the other organs like scalp, and there is some mixture of lymphatic outflow from the lymphatic outflow from the brain parenchyma and scalp and other these core structures. So there is some discrepancy between intraparenchymal flow and meningeal flow.
Thank you for a great talk. I have a very simple question. I'm wondering, is there any report about the effect of lymphatic flow on psychotropic drug clearance?
I didn't try to search for a similar item. You mean that psychiatric medication can affect brain function, and some of them, I mean, a few, the drug materials can enter brain parenchyma through BBB, and you are wondering how the drugs can be cleared, and there might be effect of lymphatic flow, right? I didn't check that. Sorry.
Question?
So thank you very much for the great presentations. So about the exercise studies. So after the long time exercise, did you find any changes in the physical parameter like blood pressure or heart rate during the sleep? Did you find some difference between before and after the exercise?
Yeah, we check these physical changes, and to be honest with you, the most of volunteers are SNU students, and they are physically stable and not obese, and so we did not find any significant changes in physical parameters like blood pressure or the body weight. They showed very similar parameters, and even we evaluated the cognitive functions in these volunteers, but they are too smart because they are SNU students. So we did not define any cognitive function changes. Yeah.
Any more questions? I have one quick question too about the exercise study. So how often did those SNU students do exercise for 12 weeks?
3 times a week.
And
3 times.
3 times a week. And how long is the duration?
We described that 30 minutes.
Wow.
The exercise was just a bicycle within the gym.
I see. It's
Yeah.
quite impressive.
Yeah.
30-minute exercise 3 times a week for 12 weeks, and you can see that change of lymphatic.
Visual was quite interesting to us, but we designed the exercise program very well. They did not do cycling, just we measured the cardiac function. So in theory, 80% of the maximum ability is optimal to improve cardiovascular function. So we measure heart rate and oxygen, the flow, the oxygen concentration, and their sweating, and we wanna check their the sustainable exercise ability.
I see. Well, thank you. All right. Looks like we don't have any more questions. So thanks again, Professor Choi.
Thank you.
Okay, our next speaker is Professor Masaki Fukunaga. He's going to give a talk titled Imaging Brain Microstructure and Function with Ultra-High Field MRI.
And I would like to thank the Professor Sang Lee and John Ho Lee, my long-time friend, to invite me about this great symposium. Yeah, today I want to talk about some studies of the ultra-high field MRI. So I just want to briefly introduce my institute, because my institute is a relatively small institute, so maybe nobody know about that. So our institute is more focused on the physiological sciences, so more basic science institutes, not belong to any university and the medical school, but it's a government-operated institute. So we are doing so mainly our institute focuses on neuroscience studies, but we also have a couple of MRI systems for the studying imaging research. And I will talk about some of these topics later. So actually, I'm in charge of the MRI facilities of the NIPS. So currently, we have 3 3D scanners and 1 7D scanners for humans. And next year, we will have another small animal scanners. So, but today, actually, we installed last year, the SIMA X system last year. But unfortunately, I don't have much data set today, so I mainly talking about 70, using 70 data set. So this is a history of the ultra-high field MRI. So development of the ultra-high field MRI is totally depending on the development of the magnet. So in the histories, so every decade, so ultra-high field means different field strengths. And I think that in the recent 10 years, or more than 10 years, ultra-high field is probably higher than 70s. So this is another graph of the development of the ultra-high field. It's a magnet. So you can see it. So development of the superconducting magnet is almost linearly increased over the years. And so very recently, well, not so recently, but in around the 2018, now 11.7 Tesla human-sized scanner is installed, and also very recently, as they got some first human image using the 11.7. So now 11.7 Tesla MRI scanner for the human is available in the 2 scanners available in the world. One in the France and another scanner in the Korea here. So this is some table about the pros and the cons when increasing the field strength. So major advantage of the ultra-high field is increasing the SNR as well as tissue contrast, especially using the tissue star. So this is based on the susceptibility effect. So you know the susceptibility effect is using for the susceptibility weighted imaging as well as board functional MRI. So I think so this advantage is giving us when we use the ultra-high field MRI. So this is a very this is an example of the example image comparing the standard 3 Tesla MRI and 7 Tesla MRI. So left hand image show the left hand image show the some SNR comparisons. So you can clearly see the 70 give us more than 2 times improvement with SNR. So this image we use the head array coils, and then superficial part of the brain, giving us a more higher SNR compared to the deeper part of the brain. But so overall, SNR is more than 2 times improvement when we use the 7 Tesla. And right-hand image shows the typical standard gradient echo image scanned by 310/70. So when you see the certain part of the brain, so low magnified image shows the about same qualities. But when you magnify certain part of the brain, so this case is the occipital part of the brain, so you can clearly see in the 70 image give us a much better contrast as well as sensitivities. So, so this is very typical example of the comparison, the two field strengths. So this is another example of the typical 3D structure scan. So this case, so we scan the 0.75 millimeter isotopic resolutions whole brain scan using the 3D T1 weighted image. So when compared, for example here, so we focus on the hippocampal structures. So when we use a 3D scanners, so tissue contrast is it's much weaker than the 70s. So if you wanna see, or if you wanna investigate some certain structure of the brain, or most small structure of the brain, so 70 give us much better information. So this is relatively small resolution in the 0.75 millimeter. So compared to the clinical situations, so the increasing spatial resolutions, we need a sufficient SNR. So that's the case. 70 is it's much better option in the kind of this case. So this is another example of the comparison of the 3T and 70s. So you know the DBS, deep brain stimulation, is one of the treatment method for the Parkinson's disease. But when you design or you plan the operations, so precise location of the electrode is very important. That means the pre-surgical planning is also very important. And so this case, so we measure the small structures of the globus pallidus. So when we compare the internal part of the globus pallidus, the internal part is also have some segment in the globus pallidus. For example, here. But the conventional image bit difficult to find. Even in the main segment between the internal and the external part of the globus pallidus. So, but when we use 7 Teslas, so this image bit difficult to find the structures, but so we found some small line in this arrow. So I think so this is another example for the give us some good information in the small structure using when we use the 7 Tesla MRI. So this is a very basics of the MRI. So this is an MRI parameters, like relaxation parameters is like a T1 and T2 and T2 stars. So this is these parameters or tissue parameters is totally depending on the field strength. So T1 and the T2 and the T2 stars. So actually, so T2 and T2 stars, this graph is it's the inverse of the T1 and T2 star. It's like R2 stars. So both tissue parameters is increasing when field strength is increased. So this is another picture or slide about the magnetic susceptibilities. So in the morning. So Dr. John Hori is already talk about this stuff. So each material has a different tendency of the magnetic susceptibilities. So that magnetic susceptibility is explained by the chi. But so when we use the tissue-weighted image, so we can differentiate. Well, sorry, so we're combining the tissue-weighted image and the tissue-weighted image, so we can differentiate this property of the magnetic susceptibilities. So sorry, I don't explain too much. So because this morning already, so John Ho is already talking about that. I just skipped this one. And so this is a typical image. So we use when we use 7 Tesla. So this is a T1 weighted, T2 weighted, and T2 weighted image. So T2 weighted image is based on the transverse relaxations. So that has some sensitive to the field inhomogeneity of the background inhomogeneity of the background magnetic field. So when they have some source of the making some disturbance of the magnetic field, they have very sensitive in the T2 weighted image. So this is some method when we measure the T2 relaxation time. So this is a very typical sequence diagram of the multi-echo gradient echoes. So when we measure the T2 relaxation time, we need a multiple image with a different echo time. So this case, we scan the 3 echo image using the gradient echo. So T2 is a time constant. Oh, sorry. Sorry, so it's a bit difficult. Sorry, so difficult to show the arrow. So T2 is a time constant of the signal decay of the T2, and so from these equations, so we can estimate the T2 reaction time. So this is another example of the susceptibility contrast when we use a T2 weighted image. So from the T2 weighted image, so we can make different images using the post-processing. So for example here, so we show the original magnitude T2 weighted image is a very left hand. And the next one is the phase image. So because the MRI is have the complex informations, so we can make some magnitude image and the phase image. And from the multi echo image, gradient echo image, we can calculate T2 or inverse of the T2 alpha image. And also, so we also calculate from a quantitative susceptibility mapping. So that one is already, so John Ho is explaining about that in this morning. So when we use these kind of the images, so just this image can produce from the single multi-echo gradient echo scan. So when we see the white arrow in the basal ganglia, so this contrast of the basal ganglia it's quite different between each images, and the relationship between these images also slightly different in the part of the brain. So for example, here in the white arrow show the deeper part of the brain is a basal ganglia or globus pallidus, and blue arrow show the white matter tract. So this relation is slightly different in the between the basal ganglia. So So T2 star show the both darken image or darken contrast in the both regions, but in the QSM show the slightly different. So this meaning that something positive susceptibility and the negative susceptibility that explained in this morning talk. So this is another example of the T2 weighted image or susceptibility contrast in the brain. So using the 7 Tesla MRI. So this again, so tissue contrast is slightly different in the each brain regions. So especially in the white matter bundles, fiber bundles, and the deeper part of the brain, the brain basal ganglia. So I go back to again this slide. And also, so this transverse relaxation time is explained by a T2 or T2 star or R2 and R2 star. So that one is very tightly tightly coupled with the concentration of the iron, especially in the deeper part of the brain and basal ganglia. So they show the almost linear relations between the concentration of the iron. And I think so this informations, R2 and R2 star, give us a physical or physiological background of the tissue contrast. And so this R2 and R2 star is also enhancing in the when we use a high field MRI. And so this is another example of the image in the multi-echo gradient echo image. So left-hand image is a typical T1 weighted image, and the right-hand image show the gradient echo image with a different echo time. So this is very typical multi-echo gradient echo image. And then from this kind of the multi-echo image, we can calculate R2 star image. So this is a calculated image. Now, when we focus on some certain part of the brain in the R2 star image, for example here. So for example here in the gray matter regions in the left-hand image. So this red arrow showed the somewhat brighter than the another cortex regions. The middle part of the middle image show the something lower contrast, even in the white matters. So you see in the T1 weighted image, they show the very uniform contrast in the entire white matters, but in the R2 star image, in the white matter show some contrast. So in the right-hand image also, like optic radiation show some white brighter contrast. So and this uniformities, I will explain again later. So this is another example of the relatively high resolution MRI using the gradient echo. So this is a 0.2 millimeter in plane resolution and 1 millimeter surface thickness. And so this is 200 micron resolution, spatial resolutions. So I'm sorry. So in this relatively high resolution image, so you can see some structures within the cortex. For example, here, so they have some dark band in the cortex. So some band is parallel to the surface of the gray matters. Then another dark band is perpendicular to the cortex. So, and so this is another example image of the SEM Tesla using the gradient echo. So previous image, so we just show the magnitude-based images. But in the tissue contrast, especially in the gradient echo image in the ultra high field, the phase image or frequency image give us a much better contrast compared to the magnitude image. So this case, so right-hand image, the phase image. So contrast between the white matter and gray matter is way better than magnitude image. So this is also the example of the high resolution T2 subjected image in the level of the primary motor cortex. So right hand image the magnitude, and the left hand image is the frequency or phase image. So you can clearly see the better contrast in the phase image. And when you magnify some certain part of brain, this case, so we focus on the primary motor cortex or central sulcus here. So you can see the omega or hand knob regions. So this is a primary motor cortex here. So this anterior part or anterior bank of the central sulcus is a primary motor cortex, and the posterior bank of the central sulcus is a primary sensory cortex. So you can clearly see such difference of the thickness as well as some small laminar structures in between the primary motor and the primary small sensory cortex. So in this image, you can see some laminar structure in the primary motor cortex. And when you compare to the another brain regions, so that pattern of the laminar structure also different between each areas. So this is another very interesting information give us when we use high field MRI. So this is another example of the high field MRI. So again we focus on the some part of the brain. So this case is the occipital pole. So this is very famous of the primary visual cortex. So when we focus on such regions, so you can clearly see there are some band structures. Here or here. So this is a very famous structure of the primary visual cortex, so-called Generis stripe. So that one is a very dense myelinated layer in the primary visual cortex. So even in the living brain, so we can clearly see there are such kind of structures in that about 5-10 minute scan using the gradient echo method. And when we even in we scan or we detect some structures in the cortex using the MRI, so we have to investigate about the fatal source of this laminar contrast in the brain. So this is a relatively old studies, but when we compare some source of this tissue contrast using a different method. So I think in these studies we performed, so the major candidate of this contrast is from the myelin lipid and iron in the ferritin, as well as the deoxyhemoglobin in the capillaries. So when we investigate the source of the these tissue contrast, we compare the histology of the postmortem brain. So unfortunately, so this is not living brain, but we scan the human postmortem brain in the visual cortex. So and then we compare the histology studies with iron staining and the myelin staining. So in these studies, so in the ultrasound image, when we scan the postmortem brain, so this contrast in the gray matter, it's very well correlated in the iron staining and the myelin staining also. And of course, some part of the brain has a slight discrepancy between these three images, but the main contrast is very well correlated of the three images. And after these studies, still we don't know about what is the major source of this tissue contrast in the MRI. Sorry, so again, so we also compared the different part of the brain. In this case, is the primary motor cortex. Again, so we scanned the postmortem brain using the 7th MRI and they compare the histologies. So this case in the primary motor cortex also showed very well correlations between the three images with MRI and iron and myelin histologies. And then so we also performed some immunohistochemistries for the staining the myelin protein and the ferritin protein, and in the primary visual cortex. So it's so you can see the generally here. So it's a slightly dense contrast in the middle layer of the cortex. So this is generally stripe. And in the both myelin and ferritin staining case, so they showed both dense contrast in this immunohistochemistries, and we also composite the two images. So it's almost perfectly match in the contrast in the composite images. That means the ferritin and myelin are very well co-localized, even in this scale. So so this just replicated the previous staining comparison. And then so we apply the iron chemical extraction to the postmortem brain tissues, and then we scan the MRI before and after these procedures or iron extractions. Of course, before the iron extraction, we saw some very good contrast in the general stripe here in the magnitude as well as the frequency and the ultrasound image. But after the iron extractions, so these procedures, so just extract iron, and also we preserve the protein structures. So that means the iron is gone, but the myelin structure is still preserved. That case, the tissue contrast in the magnitude image is very, very diminished. But still, we saw some very weak contrast in the magnitude image, but this contrast is almost gone. Even the frequency image, so they show the opposite contrast before and after. So in the after the ion extraction show the slight brighter contrast in the frequency image. So Altus are also almost diminished. So this meaning, so most of the contrast source of the Altus image in the cortex, or especially in the primary visual cortex generalist type, is come from the ion content. But so after the ion extractions in the frequency image show the opposite contrast. That means so MRI contrast of in this image is because of the signal is opposite from the previous so before the ion extraction. So that means myelin content also affect the contrast in the MRI image. So of course, so this mechanism is come from the mixture of the effect of the ion content and the myelin content. But most of the contrast come from the tissue ion concentrations, especially in the cortex. So when we use this kind of the informations, probably we can apply some Meyer architectonic mapping. So unfortunately, so it probably even in the current MRI technique, so it would be difficult to differentiate the tissue or neural body 6-layer structures in the cortex. But so in the myelin distribution in the cortex, also slightly different between each brain areas. So when we use this kind of the myelin distribution patterns, maybe we can differentiate this kind of the parcellations in the entire brain. So when we use the MRI techniques, maybe we can apply for the parcellation based on the myeloarchitectonic informations. So when you're combining the 17 functional MRI and this kind of techniques, maybe we can investigate some functional or structural relationship using even in the individual human brains. But so this relationship between the ion and the myelin in the MRI contrast is slightly different in the white matters. So this case, so myelin contrast and ion contrast it's totally opposite, but Altus show the slight bright contrast. So that relation is slightly different in each part of the brain. So we need another investigations for make sure the relation between these two contrasts. And I just skipped this one, so because this one also. So this is already explained in the morning talk. So this is also. And I just want to move on some functional studies in using the 7 Tesla MRI. So now single shot API is available even in the 7 Tesla MRI using some technique, parallel imaging technique like in-plane acceleration for the grappa and through-plane acceleration for the multiband technique. So we usually use this kind of the parameters for the whole brain scans. It's like 1.5 millimeter isotopic resolution with 1.5 second or 1 second tier. So this is quite nice. So this is some example of the resting state fMRI scan with 70s. It's quite nice. But so I already explained about that. So 7T is a very sensitive to the T2 star. And geometric distortion in the EPI also very sensitive to the background field inhomogeneities. And then, so especially for the forebrain or basal part of the brain, give us 70 EPI image or 70 gradient echo EPI image give us huge distortions. So even we can scan the relatively high resolution fMRI, so we need some technique to correct this kind of the distortions, because otherwise, when we compare the structural image and the functional image, we easily mislocate it between the two images. So, so this is another example. So when we scan the EPI and without any distortion corrections, so easily misalignment, give us a misalignment between the structure and the functional images. And so this is a very typical functional scan using something like a finger tapping. So signal change between the two field strengths is quite different. So 70s so give us a much better functional contrast compared to the 3Ts. So maybe more than twice improvement in the fMRI. So this is a very standard functional scan. So take about 5-6 minutes. Even in the 5-6 minute scans, we can differentiate the inch fingertip using 70s. So this shows the 10 different subjects of the somatotopic distribution of the fingertip in the somatosensory cortex. So this is very well replicated in each 10 subject. So this is just 5 minute scans. It is enough for the checking the distribution of the somatotopies. Again, so this is the fingertip distributions mapping. So it's quite nice. So for the standard functional, even the standard functional scans, so 70 gives us a very good contrast, functional contrast in this kind of functional studies. But so the bold contrast is based on susceptibility contrast. So that means it's a major signal source is a deoxyhemoglobin in the brain. So in this case, so large brain is a more concentrate the deoxyhemoglobin. So that's case. So the brain parenchyma nearby the large vein is very well ill by the concentration of the such kind of large veins in the deoxyhemoglobin in the large veins. So but so that means the bold contrast or functional contrast of the bold in the high field is very, very beneficial. But sometimes, so this location of the brain activity is distorted by the superficial blood flow or vein. So, and then this is another scanning method using the CBB. CBB is a cerebral blood volume imaging. So this is not the bold imaging. So CBB is a blood volume changes. So this is located in the more in the capillary part, not in the drainage vein. So that's mean. So so activation site is more close located in the changes in the CBB changes. And so when we scan the CBBs, we need some ulterior spin leveling techniques. Like in this case, we employ the basal imaging, so vascular space occupancy method. So this is more focused on the CBB changes. So when we use this kind of technique, so you can see this plot here. So red color show the profile of the signal changes through the cortex. So red color shows the peak location is more located on the superficial area of the gray matters. So this is the boundary of the gray matter spiral surface and the CSF. But blue color, this shows the signal change in the CBB changes. So they show the two peak profile. So this is a more realistic profile of the in the brain activities. So this means it's a bold technique is also good, but sometimes so distorted when we scan the more detailed signal changes within the cortex. So when we use this kind of CBB technique, so we found some changes during the motor sequence learning. Sorry, temporal prediction task. So when we performed some motor sequence with a fingertip, so we applied some task. How can I say? So we apply some regular sequence 1, 2, 3, 4, 1, 2, 3, 4, something like that. But some case, so we apply 1, 2, 3, 4, 1, 2, 3, 4, some delay we applied. Then another case, we apply very long delay 1, 2, 3, 4, 1, 2, 3, 4, something like that. So when we compare these three type of the finger movement, in the short delay case, we found some signal changes especially in the deeper part of the brain. So this means probably the short delay case, we predict the regular sequence, but so actually this case, we applied some delay between the compared to the regular sequence. That means the subject had some difference between the predictions, and then probably this case, signal changes more occurred in the deeper part of the brains. So this kind of these studies, we need the resolution for the depth directions. So this case, especially in the high resolution fMRI. So this case we scanned 0.8 millimeter resolution fMRI. So that case we need a more higher sensitivities using the 70 like ultra high field MRI. And I just go back to some 3D scanners, 3D experiment, because I already told our institute have 3D scanners. Then 1, 2, 3 scanner has a very special setup with the hyperscanning fMRI. So that means simultaneous measurement of the two subjects same time. So we set up something like Zoom conference situations in the two MRI scanners. So that we set some cameras, MRI compatible camera, microphone to project to the another scanners, and then we measure the some brain activities during the social activities like conversations. So, during that studies, so this is 3D studies. So during that studies, we found some brain signal synchronization between the two subjects in the certain part of the brain. So even in the just eye contact. So we found here inferior frontal gyrus show some synchronization between the two subjects. So this kind of the synchronization is so when we scan the normal pair, normal typical development subject pairs, we found a synchronization. But when we make a pair with a typical development and ASD case, so this synchronization diminished. Maybe this information gives us some difficulty of the social communication in the ASD case. So when we use this scanner setup, we found this kind of very interesting phenomenon in the social brain activities. So we also find another synchronization between the two subjects before and after some joint attention task. So once we apply the two subjects for the joint attention task, so before and after the brain synchronizations, so this TPJ or the temporal parietal junction and the inferior frontal gyrus show some increasing of the signal fluctuations or synchronizations. So again, so this is maybe some represent some social activity in the brains. So this is another example. So this case, so we performed some cooperations. So subject have some like grip to measure the force of the grip, and then we applied some joint force with two subjects, and then keeping some force in the together. That case also, so it's a very, very well performed pair, show some synchronization between the two brains, give us a so the very good pair of the performance of the grip, keeping the grip grip force show the better synchronization in the TPJs. So this is also another very interesting stuff that. So in this case, so TPJ as well as IFG show the very important functions in some social brain activities. But in the TPJ is a very complex structures, so still we do not know about that. And then we applied some 70 to investigate this part of the brain. So we just applied 70 diffusion image, 1.25 millimeter isotopic resolutions. It's a relatively high resolution DTI. And we made some probabilistic connectivity in using such kind of the DTI dataset on 78. And then we compare the functional connectivity using a resting state fMRI on 70 and the structural on 70, connectivity on 70, and they investigate some connections between TPJ connection between the another brain regions. So when we apply these studies, we use this template from the Human Connectome project. So TPJ region has separated in the 5-6 area in this atlas. So for example here, so TPJ is slightly separated in the 5-6 regions in this atlas, and we compared functional and structural connectivities in each brain regions in the TPJ. So in the FC show the functional connectivity, the SC show the structural connectivities. So, so you can see this, so this red circle show the target region or seed region of the connectivities. So in FC and SC, both of them slightly different, but very well co-replicated in SC and FC. This case also very well, something very well correlated. But so each brain region shows this, it's totally different distribution of the connectivities within the, even in the single TPJ. So they showed so the slightly different distribution in the connectivities. So this is the example of the distribution of the connectivities in the each region in the TPJ. So it shows slightly different distributions. So this is based on the pasteurization. But when we focus on the more detailed connectivities based on the each vertex, so vertex is a kind of the voxel in the brain surface. So green dot show the seed region of the point source of the seed regions. So when we scan, so for example here, so this case the PF regions. So we just move this source, seed region of the within the PF ROI. So we show some image here. Even in the single ROI, show the it's quite variation, big variation in the connectivities. So I think it's this kind of the detailed studies or detailed structure study or connectivity studies, 7T give us a better chance to do something like these studies. Sorry, I have much slide here. So I just wanna explain slightly more about the NHP. NHP meaning the non-human primate. So for the animal studies, so of course in the small animal like mice or rat, probably we can use animal scanners with a very small diameters in the magnet. But a relatively large animal like macaque monkeys, we have to use like a human-sized scanners. Otherwise, it doesn't fit the brain in the MRI scanners. So in this case, we also use a human CT scanner for the measurement of the macaque monkeys. So we made some dedicated RF coil for the macaque monkey measurement. So like a human scan. So we made some 24-channel array coil for the macaque monkey brain scan. Yeah, something like that. So even in the macaque scans, so we perform something like HCP studies. So we can scan the functional structural connectivity or pasteurization using the T1 and the T2 weighted image, something like that. Sorry, so I don't have much time, so I just skip this one or this one. And so this is an example of the 70 macaque monkey studies. So in this case, we use the optogenetic stimulation. So this is a method to directly stimulate the cortex neurons. So using the optogenetic technique. In the monkeys, so this kind of technique is still a bit difficult. So we need a much special technique to induce the sensitivity of the laser stimulations. So this is some example. Sorry. So this is some example. Okay. So when the LED light is become bright, we stimulate the motor cortex, primary motor cortex. So we can induce the finger movement using the optogenetic stimulations. So we scan the anesthetized monkeys. So with this setup, so we can see some brain activities during this kind of the stimulation, during the stimulation. Of course, if you focus on the stimulation side, maybe we don't need an MRI. So maybe light microscope or microscope technique it's much better, give us much better information. But if we want to see some remote site, so we need some technique to scan the entire brain. So this kind of the case, I think the fMRI give us better information, something like these studies. I just skip this one. And of course, in the 70s, give us not always give us a benefit. So still we have some technical difficulties. So for example, SAR for the safeties, or sometimes it's too short, and T2 star give us signal dropout in some brain regions. We need some technique to minimize this kind of the difficulties. But so if we use the 70 MRI, so combination of the 3D or other techniques, maybe so the 70 has give us a much better information compared to the conventional technique. So not only for the basic research, I think in the now clinically applicable for the 70s and clinically applicable. So accumulation of such kind of clinical knowledge maybe that give us another application for the 70 MRI. Oh, thank you very much for the giving me this opportunity to show some recent study of my institute. Thank you very much for your attention.
We're gonna take a couple of questions.
So one of my questions is, I know you develop a lot of techniques that you introduced today, but you also have a lot of collaborators across Japan, as the center is, really designed to support the collaborative research in Japan. How do you really make them to work on these cutting-edge techniques? Usually, many of them are not really exposed to the new technology, and oftentimes they are unwilling to use the new one as compared to 3 millimeter isotropic voxel fMRI.
So sometimes it's a very big challenge to explain how benefit. So 70 gives us how benefit, but so I take some time to explain more details about some good and bad in the high field. Of course, I think not always 70 is better than 3D. 3D gives us much better information sometimes, especially for example, for brain or the better part of the brain. So generally, we spend some time to explain some better, good and bad in the different field strengths.
Hi, thank you for the fascinating talk. What I wonder is, I heard from a colleague, I haven't been into a 7T scanner, but the difference between a 3T scanner and a 7T scanner is that with a 7T scanner, you get more headaches and it takes a bit of longer time. And the noise is noisier. But I was wondering for how it is for animals, like the monkey, for example, how would it be for them if they were scanned through a higher magnetic field? Would they have headaches after anesthesia?
Okay, so generally, so we don't feel any headache give us. So when we move, so it's a patient, it's a subject in the right on the patient tables. When moving the tables, so subjects sometimes feel some dizziness, especially in the very close to the gantry of the magnet. because so field gradient is very steep in the countries, in front of the countries. So, but so in our case, so in our institute, about 50% of subjects feel something during the table movement. But once so subjects stay on the 70 field in the about the center of the magnet, maybe 15 seconds, 20 seconds after that, so that feeling is gone. So most of the case you should okay. So my case, so, maybe less than 0.1%. It's 1 per 1,000. They quit the experiment, but most of the case, even feel something, but still okay. In the animal case, it's quite difficult. But in the my friend in the another institute, they use a 9.4 Tesla MRI, and the subject, so they scan the marmoset monkeys. When they move the very quickly moving into the magnet, so marmoset has some vomiting. So they have some effect in the animal also, but I'm not sure how can check the feeling of the in the field strength, but they have some effect in the marmoset in the also.
That's sad.
Yeah.
Thank you.
But when we move very slowly, it's okay.
Do we have any questions online? Okay. All right. Go ahead.
I think hyperscanning approach is very interesting. Are there any challenges, technical challenges or drawbacks conducting this type of imaging method?
Okay, I think technical challenges in the synchronizing everything so it's sometimes very difficult for scanning or presenting stimulations or the subject response. So we have to scan same time and correctly. So it is sometimes difficult. But once we built the system, it's okay. I think most difficult point is we found the subject same time. So we need some certain pair of the subject. Sometimes it is not seen some subject not coming the institute. So we just canceled both my experiments. So it is some drawbacks. But in general, it's quite similar as the single fMRI scans, I think.
I have a question. So do we have any available Milo architecture parcellation-based LS?
Atlas, yes. So they have some, they already opened the brain parcellations based on this kind of susceptibility contrast. So I couldn't, I couldn't precisely remember that papers, but already opened some data set based on this such atlas using the susceptibilities.
Thank you. All right, since we're a bit behind, we're going to start right now. Just a quick announcement. We have a lot of leftover food, so please help yourself and bring some, especially those grad students here, before you go home, right? Okay, so we have two more presentations before the end of the session today. Our next speaker is Professor Jiuk Cha from SNU Department of Psychology. He's going to give a talk titled Large Brain Models for Neuroscience. All right, take it away, Professor Cha.
Can you hear me okay? Hi. Good afternoon. My name is Jiuk Cha. I'm from the Department of Psychology. At SNU, I work across psychology, of course, and also brain, cognitive sciences, and programming in AI. So today, so the title was originally large brain models, but it could be interpreted as a foundation models for neuroscience. But before I get into the talk, let me start with why we do science, why I do science, and why this line of work matters so urgently. So Korea faces two challenges that actually threatened our society's very foundation. And we have the world highest suicide rate and the lowest birth rate in recorded human history. And these aren't just statistics. They represent profound mental health, mental wellness issue in this country and demographic crisis. And now you might be thinking, how does the brain imaging or neuroscience connect to these massive social problems and challenges? And that's exactly the question that drives our work. Can our work be any useful to address these kind of questions? We believe that understanding the human brain, human behavior and psychology, and not just understanding, but also predicting developmental trajectories of mental illnesses, and developing early intervention for mental illnesses could be part of the solution. But to this end, we need a breakthrough in how we analyze, how we approach and interpret the brain data, brain imaging data. I think science and technology can be our hope. So 4 paradigms of science, from left to right: trial and error, empirical science, theoretical science, computational science, and we are now entering into data-driven science, or AI for science, how you say. But this 4th paradigm is interesting. If you see the brain, those circuit patterns, this isn't just another. This may represent a. This is not my drawing, but it may represent the AI or machine learning or general artificial intelligence, and these are not just another tool for science. I think it's a quite different one. It's a thinking partner, right? For the first time in human history, we have the machines that don't just calculate or simulate, but they can reason and discover. They see the patterns that we miss, and they ask questions we never thought to ask. And here's what excites me most as a scientist, as a neuroscientist: we're not being will not be replaced. We'll be empowered by this data-driven science, new approach. So that's our hope. Well, this paradigm shift illustration shows a fundamental change in machine learning or AI technology, AI methodology. In the 2000s, feature-centric approach, machine learning based on extractive features dominated. In 2010s, they introduced model-centric paradigms, deep neural network, pre-trained architecture enabling transfer learning across multiple domains. And now it's a foundation model, era of foundation models. These models represent a data-centric revolution. A single generative system, models can be adapted to many different tasks without task-specific laborious retraining. Few-shot learning or even zero-shot learning became possible. So this progression from specialized to generalized intelligence or generalized artificial intelligence mirrors the broader scientific paradigm shift and the implications extend beyond the computational efficiency. We are now witnessing the emergence of AI as a universal scientific instrument. So look at the convergence of evidence. Nature journals declaring AI for science, defining events, something like super fast supercomputers dedicated for scientific research, just launched last year. And through this is just one example, but through this we're witnessing unprecedented computational capacity. And the last year's Nobel Prize in chemistry validates what we suspect: AI-driven protein structure prediction. This represents paradigm-shifting science, as we all know. And the data trajectory is noticeable. 175 zettabytes by 2025, exponential growth. Then that the traditional analytic methods could other methods cannot even process. And the Trillion Parameter Consortium, this is a global consortium representing coordinated global investments in foundation model for science. And for science, I think it's we're entering the new era. It's a golden time. We should be going up soon. A few examples outside of the neuroscience for AI for science. AlphaFold, the Nobel Prize-winning breakthrough, right? This model can predict now protein folding from amino acid sequences, solving a decade-old challenge in the structural biology. EVO2, developed by Stanford Group, is another foundation model trained on 9 trillion nucleotides across all domains of life, with capabilities from gene function prediction to genetic circuit design. In human behavior science, Kentaur is another foundation model. It's a model retrained or fine-tuned on the relatively smaller data, but people start to call this as a foundation model too, because it captures how people make decisions, and the model can generalize to new cognitive tasks, cognitive domains that has never been trained. So few shot, zero shot learning capability emerges. So what we do in science is ultimately boil down to model fitting, right? Model comparison and model selection. So traditional models, as we all have used, simplify reality, and these models make it human interpretable and help us explain what happened. But AI models for science is different. They do something completely different. They don't just explain, they recreate reality itself. And if you notice this quote, to understand is to create. This is an exact quote, but this is kind of the rationale of using AI for science, because it can create something useful. Maybe it's not a complete understanding of something, but it's a different approach that can be potentially more useful than at times than traditional models. So I'm sure you all know what foundation model is, but let me briefly introduce the core concept. It's fairly simple. if you train a model, most of the time, transformer model, on massive data without any labels, and it used this fill in the blank approach, right? So, for example, if this is data, my neighbor gave me apples, so I said something, and the model predicts what it follows, right? It understands the context without any explicit instruction. Not just the grammar, but also the context, the syntax and the context, and the entire content. So no labels needed. The model learns from the structure, from the data. And once it's trained, it adapts to many tasks that it has never been trained on. So what makes foundation models successful? 5 key properties. Expression, flexible information representation, and scalability, handling massive data efficiently, and multimodality, connecting different types of domains, and compositionality. In Korean, it's 융합성, right? 합성성. It combines elements for holistic understanding. And the memory, of course. It can store lots of information and use the learned knowledge. And here's the two secrets of the foundation models that they have discovered. By they, I mean computer scientists. The first one is scale. Performance scales as a power law, as a function of the compute time, data set size, and parameters. I'm sweating, so I need to. And the graph from the OpenAI's work, 2020, shows something remarkable. I mean, it's natural to us now, but at this time it was remarkable, as they say. So model performance keep getting better. What you see is test loss. So the smaller the better. And it keeps getting better as you scale up. Of the scaling those 3 key factors, and they haven't hit a ceiling. So model keeps improving. And the scaling law drives hundreds of billions of dollars in GPU purchases, data purchases, and so on, because it works. And AI developers keep investigating in more data, more compute, more parameter, better, bigger models, because this power law tells them it will work exactly to what extent. But scientifically, we still don't fully understand why this works, why the rationale or the mechanism of, the mathematical mechanisms of this power law scalability. But this has been the secret for the foundation model. The second secret is emergence. As the model scales up, they suddenly develop abilities they were never explicitly trained for. It's a phase transition, not a gradual incremental improvement. And this brings up to the next, to the question driving our research. Can we achieve this kind of emergent abilities in our brain modeling if we were to build really powerful large brain models. So if scalability and the emergent ability work for language data or image data and protein sequence data, what about the brain? We think that large brain models could be the next big thing. We have thought that for a few years now. And this may help analyzing brain representations, interpreting cognition and behavior, neurological and mental disorders, etc., and predicting trajectories of the certain conditions. And to make this happen, we need massive computational initiative. That's why we come up with this international collaboration team, NeuroX. It's our collaborative research projects with computer scientists at some of the national laboratories in the US. So through this program, we secured access to the world's largest supercomputers at Argonne, Oak Ridge National Lab, and NERSC. With these resources, we're building scalable brain imaging models, brain transformers. So, what I'm gonna talk about is our recent model developments for the fMRI and the large pre-trained model for the electrophysiology. We have put most of our major effort on fMRI. So how do you build efficient neural network, efficient transformer for brain imaging? This was our first question. And we started with the specialized transformer architecture called SWIN transformer architecture. And this was originally developed for image data and video data. And we adapted for the unique spatial-temporal structure of the fMRI. It's a 4-dimensional structure, as you know, right? There wasn't a transformer that can be applied to 4-dimensional data at the time. So this joint work done with Professor Moon at SNUBIC represent our first work. The key innovation, the key undertaking was to treat fMRI as a 4-dimensional video. So 3 spatial dimensions are X, Y, Z, along with the time axis. And using hierarchical attention mechanisms, as you can see on the right, that can capture the complex patterns of the spatial temporal fMRI data at the multiple scales, not just voxel level or system level, but from the voxel level all the way to the entire system level, covering the whole brain networks without any dimension reduction techniques. And so this is essentially an end-to-end fMRI transformer model from raw fMRI data to predictions without any handcrafted features. And the question was how well this model could work. And if you look at these results, three different rather simple benchmark tasks. So we started with the sex classification, age regression, and intelligence regression. By intelligence, I mean NIH toolbox. And our model, dubbed SWIFT, versus traditional models and deep neural network baselines were shown. So blue bars show the consistent outperformance across every single task. And it's done in human connected projects and ABC data across this data, the pattern holds. Transformers can indeed learn something meaningful, as we found. And this is the visualization of the spatial patterns of the learned representation in the case of sex classification. We used a post-hoc model interpretation tool. The swing transformer doesn't allow us to look into the spatial patterns or representation directly. We have to use another additional post-hoc model for the model interpretation. But this shows some patterns that contribute to the sex classification task. We can do the same thing with the intelligence task, age, or depression, and so on. So in this first study, this is not a foundation model. It's a pre-trained model at best, right? And we first presented the potentially very powerful end-to-end transformer for 4-dimensional fMRI data for the first time. This was published in EURIPS. So it was an encouraging beginning, and now we're trying to upgrade this model, or scale up this model, and upgrade its strategy into self-supervised learning. So the first upgrade, first undertaking was designing self-supervised learning at scale. We've been doing masked image modeling. Essentially, this is a fill in the blank using the 4D fMRI data. We mask out some parts of the brain, 3D volumes, 3D squares, and then train the model to predict what's missing. And we're doing this on the largest scale in terms of the data, including the UK Biobank, ABCD, HCP, and other data. So this should be our largest pre-training efforts. And the second upgrade to this model was to enhance, to improve the temporal dependency of the representation learning. So brain states evolve over time, right? And these temporal patterns should be learned correctly, but as this is our Swift model, fMRI swing transformer, published in EURIPS. After our publication, in our analysis, we found that the model doesn't really capture meaningful temporal dependency. We didn't know that because we used we didn't notice that because we used the resting state data. And as you know, in resting state data, the temporal structure is not always obvious. But in our autocorrelation analysis, we found that our model here, the autocorrelation function results shows that our model, the autocorrelation, the temporal pattern, temporal dependency pattern doesn't really match to the data that it was trained on. So there was a mismatch. So to fix this problem, we made 2 changes on your right. First, encoding relative time distances, not absolute positions, using lottery position embedding technique. And literature shows that this new way of positional encoding may help the model understand temporal context better. And the second, to learn temporal flow first, using temporal attention as separated from spatial attention module. So learn the temporal pattern first, and then learn the spatial patterns. That was the idea. And as a result, we found our new model, upgraded model, shows much better match to the fMRI, the actual fMRI autocorrelation. So embeddings of this model now is better match to the the actual autocorrelation of the fMRI data. So with this model, with these two upgrades, so we wanted to test whether it actually really worked at scale. So after massive self-supervised learning, pre-training, we did systematic scalability experiments. If you look at this, the figure on the left, this is our scalability plot. So model performance as a validation loss as a function of amount of compute. If you see the best performance, the lowest point here, the different color shows the different size of the model. The size of the data is the same, but only the model size differ here. So if you see the best performance here, it actually improves as a function of the model size here. I have a different figure showing the scalable improve, but if we analyze this, the highest component, the lowest point, it actually follows the power law scalability pattern, but it's only 3 or 4 data points, so it's power law doesn't mean too much here. But we found the performance improves with scale. But the red line, our biggest model, 3 billion parameter model, shows actually worse performance than 800 million parameter model. So this wasn't our expectation, and as we interpret this, we may hit the data wall, data bottleneck here, and this model, the largest model, is so hungry for more information, but our data set doesn't really fit any more information. So that was our discovery. This was is unpublished yet, but we're working on the paper. But what about their performance in the downstream tasks? If you look at the right, so it shows the adaptability of our pre-trained model. If it shows great adaptability, then other people can call this as a foundation model. Oh, I already say it's foundation model here. But so we're testing this on the tens of different downstream tests, but I'm showing here only the result from 3 downstream tasks because we're still working on it. But at least these 3 completely different domains and 3 completely different data, the data that has never been seen by this model, we show some level of adaptability. The data is fairly small. AD conversion is from ADNI. We only use less than 100 data. The second data, pain state classification, is Dr. Woo Chung-wan's data published in Nature Medicine, 60 or so subjects. Antidepressant responses, this is NIH's EMBARK data, 150. So fairly small data. With this size of data, no one can train a meaningful deep neural network without any pre-trained model, right? So our idea is whether our pre-trained model shows good practical utility in these settings. So across all domains, our model Swift version 2, the upgraded version, outperforms the current SOTA model, Brain LM, published in iClear, Brain Jetpack, published in, I think, CVPR. So far, so good. So the bottom line is that we've proven scaling low works for the brain models to a certain degree. There's a ceiling point, as we found, and our pre-trained model show the capability of few-shot learning. I need to be cautious about my wording because it's not so few. It says tens of samples, so 10-shot learning capability. But it's encouraging. So I think we've identified our path forward. We need more data. So in another study, we asked, can we apply this swift or fMRI transformer approach to entirely new populations, like baby brains? So we tried newborns. The data is from UK Developing Human Connectome Project. So newborns with 4 to 6 weeks old, and these are their brains, the result of ICA on your left. Our transformer, the same Swift model, it's actually before the upgrade. This transformer model trained on 500 newborn data, resting state fMRI, well, actually sleep state fMRI. We wanted to test whether the model can predict their future stages of cognitive skill, language, and motor development in their age of 18 months ahead. And the result is, if you can see those red bars, that's our model winning other baseline models. The conventional baseline models based on functional connectivity features. So in every category, our end-to-end fMRI transformer outperformed. So if this really works, this can lead us to very efficient early detection of maladaptive development, right? And this may be able to give us a little bit of hope this may give us, clinicians and families some time to intervention, early intervention. Another application of our approach is that the question we asked the question: can we predict how human brains respond to a certain cognitive tasks based on resting state data using this technology, fMRI transformer technology? And if you look at these 3 individuals on the left, each has a unique brain activation pattern. This is a GLM maps. The actual GLM maps during the social cognition, like theory of mind, this is HCP data, aligned with the predicted task maps based on using traditional machine learning, rather simple machine learning techniques. This is a 2016 science paper. So we wanted to do the same thing using the similar data, same objects, but with a different technique, different technology. So again, we leveraged our Swin fMRI transformer Swift, and we additionally implemented a decoder that can generate a 3D image, the brain-like image, looking like a GLM result, GLM maps from a task fMRI. So this part, left part, is the same fMRI swing transformer integrated with this unit transformer decoder for the 3D image generation. So if you look at this, the results, so our fMRI transformer integrated with unit transformer is called SUI-FUN. This model outperforms other SOTA models by 12% the performance gain on predicting task activation maps. This was done in UK Biobank data, the using task fMRI data as an output data, well, outcome label data, and resting data, resting fMRI as input data. So on your right, this shows activation maps that are responding to the face condition, face versus objects. And if you can see, there's a person-specific picks, well, significant voxels, right? There are some commonality across subjects, but also differences, individual differences. And our model reproduce each brain's fingerprints of the fMRI response, well, brain response to stimuli. And the GLM results are in blue. Our transformer prediction is in red. Yellow shows the overlap. And what is interesting is that we use this the predicted activation maps and test whether these maps can forecast individual psychology or psychological states, because this face versus objects might represent their general emotional responses, well, responses to the emotionally charged stimuli that may capture individuals' psychological states. That was the idea. In our experiment for predicting depressive symptoms, our model shows 60% improvement over the SOTA model or the actual real fMRI data, task fMRI data, GLM maps. And for predicting neuroticism, we found twofold improvement. So this study shows that our end-to-end fMRI transformer can actually capture individual brain functioning with the brain activation map prediction task, and even mental health states. Presumably, this information is already embedded in their resting states, and those information contribute to this activation map reconstruction as well as predicting psychological outcomes. So these are all good, encouraging results from the fMRI transformer architecture, but they have some fundamental challenges, limitations. Transformer has lots of limitations. So, and to address those, some of the fundamental limitations like computation inefficiency and challenges of interpretation of the embeddings, for example, we tried something else. We started to try something else very recently. We start to look into this new dim neural network architecture state space model. called Mamba, and to test whether this idea could be useful for potential foundation model for fMRI. So our fMRI transform model, swing transform model, uses this hierarchical grid-based models, grid-based approaches, and this approach, prior model here, this approach, ended up wasting up to 60% of computational resources to process empty space background voxels. So for this Mamba, we focus on only brain tissue and ignore the background. And also using this Mamba backbone, state space model backbone, we wanted to take advantage of the computational efficiency compared to the transformer that requires excessive computational complexity to calculate the attention metrics. So with this new implementation of the new technology, Mamba, we use the same data, same task, and same computational resources, just changing the Mamba backbone, switching transformer to Mamba backbone. And we found the very first pilot study shows this kind of performance. It's a promising initial results. So achieving 98% of accuracy in sex classification. Of course, sex classification is the easiest task. This is sort of our positive control task. If the model fails at this, the model doesn't learn anything. But as you can see, it learns something. And now we're testing this for the more challenging downstream task, as well as to the naturalistic fMRI data, where more meaningful temporal dependency, temporal structures are obvious. Another foundation model, another line of work is a foundation model for ePhys data, electrophysiology. And this is our first step, thanks to Professor 정천기 교수님. We're collaborating with him. So the EEG, the human electrophysiology I'm talking about, EEG and intracranial recordings. These are the direct, as opposed to indirect fMRI pulse signals, direct electrical signals from the brain. So the goal is, again, leveraging the scalability. We want to build our team want to build the world's largest foundation model for human brain electrophysiology, both scalp EEG and intracranial recordings. The challenge, the first challenge was that because of the different recording setups and scenarios, these recording, this kind of scenario have a different, channel configuration of the ECOG and EEG, and different positions and different numbers of electrodes, channels. So we need to come up with a good way to normalize this and to process this data in a meaningful way. So how do we train a single model that can work across all of this data, So the solution was the new positional encoding technology called spatial temporal conditional positional encoding. So basically we encode the relative spatial data, relative spatial and temporal positions of the channels, so the model can learn from the context regardless of the specific configuration. This is a more generalized way of learning spatiotemporal patterns. And then we use combined spatiotemporal attention to integrate this positional information with the actual brain signal data during learning. And the results, this was our first result. This approach combined with the self-supervised learning, fill in the blank approach, we were able to achieve that almost SOTA performances in these limited benchmark tasks, but with only 10% of the training data that other SOTA models use. So this proves that the data efficient learning is possible with our model, with our approach. So that's 10 times more data efficient learning. So we were able to present this in a workshop. So it was a quite encouraging first step. And then now we've been working really hard to scale up very aggressively with the world's largest multimodal electrophysiology dataset. As you can see here, there are so many co-authors, first co-authors. I think 5 or 6 are first co-authors collaborating with Professor Jung Chun-gi and Dr. Shinjae Yu. So we have been collecting 155 terabytes of EFES data, EEG and ECOG. We're testing the models from 5 million. Yeah, it doesn't show here. 5 million parameter model to 1.8 billion parameters. It's a 300-fold increase. And the results is that we're reaching the state-of-the-art performance. As you can see in the left, these are something like 20 different benchmark tasks. We're reaching the SOTA performance in many downstream tasks. So red line here is our model, DIBER. So model works and scalability. Well, it looks like model works. It's not always the top performance, but it's working now. And the decoding, well, the downstream performance is one result. Another more important result, I think, is the scalability of this model. So for the first time, we quantitatively demonstrate this kind of scaling low as a function of, so model performance as a function of compute, data size, and model size. As you can see, there are some meaningful increase in performance or decrease in these plots, right? And it follows the power law. You may notice that the plots are log-log plot. So linear fit in the log-log plot is power law. This has never been shown in the EFES foundation model to this level, to the level of this kind of massive compute and data size. And also we quantitatively demonstrate this scaling low, not just those 3 factors, but also across different epochs. So that shows data constraint scaling low demonstration here. Performance as a function of epochs. So with these kind of contour lines, what this really means is that it's a practical message to come up with the best recipe to train an effective model, combining those 3, or actually 4 key factors: amount of compute time, amount of data size, amount of model size, and also amount of epochs. How to optimally allocate the GPU time across those factors. So this line, for example, shows our best practice, the best recipe that can achieve the best performance with this constrained condition. So this kind of best recipe is what data scientists or computer scientists have sought to discover. So it's still going on. The work is still going on. We want to even scale up the model and the data even more, and to see what happens in our downstream tasks if we see any emergent abilities of our models. So I'll try to wrap up with the talk with this next few slides. What we can see here is the large language model. And I think this might be considered as a left hemisphere of our brain of a humankind, for if I may say. So LLM enables language understanding, of course, processing, logical thinking, and reasoning. We're all using it for our scientific research. Based on text data, right? Based on the model that used transformer architecture. So yeah, this works. The functionality of this capabilities enabled by the LLM might be considered as the logical left hemisphere of the brain. But on the right, large brain model might be something different. Language model give us the words, and the brain models give us the silence between the words. The hesitation before you speak, the emotion that I feel now, the unconsciousness bias that shape your next decision making. So I think our generation has, with LLMs, we have built the AIs that think and speak like a human. And if we can build another model, the large brain model, this model can understand the language of the brain syntax, and the brain. This model may be able to help us understand the unspeakable thoughts, non-verbalized thoughts, intuition, cognition, memory, and so on. So if these two models can be integrated in some way, this might be a really cool completion. So the future of AI, or AI for science, may help us understand human brain, human language, and behavior inside out. So that's our vision, and with the time, I need to skip this. Basically, we are doing the first form of integration of LLMs with the LBMs, using what is already established vision language model approach. But this is just a start. This may not be the end state. We're exploring different techniques, different ideas. So let me leave you with the 4 key messages here. First, foundation models work for brain imaging. It helps decode brain cognition, emotion, behavior, mental health from fMRI. Perhaps not just from fMRI, but from MRI in general. And second, scalability matters. With these 3 key ingredients: data, models, and compute. well, in some experiments we have already hit the ceiling, but there's a possibility of feeding more data. So if we can fit more data, we may not. We may see the scalable increase of a large brain model as we have shown, as we have seen in LLMs. And the transformer and other foundation model architecture will allow really interesting multimodal integration, connecting the brain to genetic data, to behavior data. As I show you, there's already a foundation model for behavior data, which can be naturally integrated with the brain model and the clinical data, of course. This will allow come up with a unified representation. And if we link LBMs to LLMs, this may give us the next breakthrough. So with this, I'll stop. I'm happy to take any questions. Thank you.
Thank you, Professor Cha, for the great talk. We have a couple minutes for questions. Anybody has any questions?
Our time in developing the structural foundation model for the brain, and we successfully submitted the ISMRM abstract yesterday.
Oh.
So I'm very happy, very excited about your work. The challenge for us is, as compared to this, like 3 million slice trained foundation model that we developed, the performance gain was pretty small. It's more
Very
like,
small.
like 10% gain as compared to the one that was, trained from the scratch.
Mhm.
That's, think about the efforts. We spent like literally, I forgot the number, but 2 weeks of time just for the training the foundation model with this whole number of data sets.
Mhm.
Gaining 10%, that doesn't seem right. What was your experience with it? And how accurate is your prediction? Like, for example, if you're doing binary prediction and your chance of just, randomly, getting the correct answer is 50%.
Mhm.
If if your model performance is like 60 or 70% by training all of these data sets, that's not really a good performance, right?
Mhm.
It all depends on the question of what kind of task you are doing it. But overall, you have compared a lot of different tasks. And what is your
Yes.
impression of this?
I mean, it's not efficient at all. Of course, it's not cost efficient at all. We have, I mean, it's not our cash amount, but the amount of compute time that we have burned last year is here, which 560,000 node hours. Each node has 4 to 8 GPUs, so it's millions of GPU hours worth 10 million USD.
Yeah.
If we were to use Amazon Web Service, for example. And our best performance gain in any downstream task is usually 20-30%.
Okay.
That's our nature moment, right? But it's not cost efficient at all. But as a scientist, we wanted to test the idea of scalability. If the brain data shows a similar scalability in terms of the data size and model size and compute time, this may give us a new idea for the path forwards. Maybe it's not efficient yet, but if this model can be integrated with other types of data, our approach is very simple, very dumb. We just use resting state fMRI. We didn't really leverage the rich metadata of that can be obtained in any individual, like cognitive behavior data, genetic data, self-reported data. That those data haven't been touched at all in this model approach. we just fed resting state fMRI. So it's, I mean, our approach is not designed for cost efficient or to maximize the impact of the cost. We simply wanted to test the scaling effects, because that scalability studies have helped a lot of future studies down the road. These scalability plots in 2019 or 20. And the meaning that the scalability follows the power law means that in order to see a small gain of performance, you need to increase your input order of magnitude, 10 times more, 100 times more, 1,000 times more. So it's not, I mean, the scalability itself is not cost efficient at all. But it works if we can provide all the unconstrained resources, which is not very realistic. Yes.
Thank you for a very interesting talk. I guess in relation to the last part of your talk, where you're talking about combining large language models with this brain model. I guess my question is, why would you need to do that? I mean, I could see it could be convenient to do it, but in principle, if your brain models are capturing language processing as well as higher order cognitive processing, then maybe you don't need the large language model at all. I mean, you'd kind of want to just train the model on data that has those kind of task-related cognitive processes incorporated into it. So I guess that's my question.
Yeah, I mean, the idea is we want to leverage the power of LLM, because our brain model is not as powerful as the LLM. And our data, we know that our data is, so many issues, right? SNR, physiological noise, which may not be ideally taken care of by simple or simplistic mass image prediction training. One way is to make this large model approach more sophisticated. And another way is to leverage the power of the LLM that can infer from different sources of data. They can understand for example, the literature knowledge and use those literature knowledge to analyze the actual data. That kind of ability we couldn't achieve just by using brain model. But yes, ideally, brain model, if the brain captures the fMRI or EEG, captures all the necessary cognitive processes, ideally we want to be able to extract those information directly from brain data using brain model only. But as Professor Jong Lee says, our model is not that smart yet.
Okay, we're going to take one more question.
Oh. Hello. Yes. Is it me, right? Yeah. Thanks for the interesting talk. Yeah, I think a lot of people working on this. Just thinking about why it works or doesn't work. I think large language model works. I think for a lot of different reasons, because of the information we have in the text is actually capturing the information we want. I think it's already a big, tall, I would say unknown to say that brain imaging are capturing information we actually need. I think that itself is a big question. Okay. So I think that's for me is the biggest reason why this is not working yet. Okay, so that's a completely different situation, right? I think
Right.
I think natural language processing, with data we have, has worked to already a large extent pre the world of LLM. Of course, with a newer technology, we can do far better, right? But that's a different situation. I think we don't really have that. We're not in a position with brain.
Right.
I think that's information logic. It's not there.
That's very sharp comments. In some of our data that has multiple run fMRI sequences, we did that. We analyzed the noise ceiling of the multi-run fMRI data, and whether the information that we capture, we extracted using fMRI transformer is comparable to the noise ceiling, and it looks like we are already reaching the noise ceiling. So with the fMRI, the task fMRI generation task, what we have, what we are seeing in our model for performance already reaches the noise ceiling. So that's, I think, the information most of the information has been already extracted from using that model, and that's I think that's the ceiling of the information content that we can model, which is not which is what I'm trying to say is that if information content embedded in resting fMRI data is so little that even I shouldn't say suboptimal, but even our current state of brain model can already reach the noise ceiling.
I get that. So just follow up. The second question, I think, just goes back to your definition of foundation model. I think it's slightly strange. If you go to your very early on, you're talking about these three paradigms of machine learning from, I think, that's one. So I think, to me, I think, I guess if most people think of foundation model are the one where you pre-train with no labels or self-supervised pretext tasks, and then you fine-tune them with downstream tasks. I cannot imagine any zero-shot learning, because if you don't even know a question being asked, you don't know what to do. Even with an LLM, you have scale AI being paid millions to do those downstream tasks. Okay, so I think that's sort of really in the what you call the deep learning bucket. So I would just sort of that terminology, I think I'm not quite agree.
Okay.
Yeah.
Can I ask a question? Hi, Dr. Tsai. Thanks for the great talk. I have one question regarding how your models actually deal with the overfitting problems when you are dealing with small data. So maybe can you tell me, like, when you are fitting your Swift or Swift version 2 on a small data set, like the data from the Dr. Sungwon Woo, the sample size was around hundreds, right?
Right, less than 100.
And then what was the number of parameters that you have to fit in your...
the number of parameters is hundreds of millions and billions. Right. So over parameterized model.
Right, and it's not a problem for the Swift or Swift version 2, right?
It's not problem if the model has adaptability, and we show some level of adaptability even with the. So we try this scenario to extreme, using 10 sample fMRI data. Can our model show useful adaptability? In some tasks, yes. Some no. But what we're seeing is that in the challenging tasks, in the sample size of around 50 to 100, the model can easily outperform traditional machine learning models, and our model perform better than other pre-trained deep neural networks. So yeah, in general, pre-trained models can be fit to small size data.
Maybe you could tell me a little bit more about what do you mean by adaptability of the model?
Oh, if the pre-trained model doesn't have any information, like random information, right? The model does not. The model will not give us any benefit of the model does not have any transfer learning capabilities, right? If the model, this model weights has any useful information, it will allow us to fit even such a small data, and that's exactly what we have found, what other have found. The pre-trained brain models has transfer learning capability. The question is to what extent, to what magnitude.
Okay, thank you very much. All right.
Yep.
Thanks, Dr. Cha.
Thank you.
Let's finish through. Our last speaker is Dr. Benjamin Schmidt. He's going to talk about exploring new frontiers in MR research with SIMA-X.
Thank you for the introduction and for the opportunity to speak to you tonight. I guess I'm the only thing that stands between the audience and dinner. My name is Ben. I head up our research and scientific partnerships division for Asia Pacific and Japan. So I work very closely also with our Korean collaboration team. And it's a real pleasure to be speaking to you about, after hearing so many very inspiring science presentations, to speak about a bit more about the tooling, right? The Magnetom SIMA-X, really the world's most powerful scanner in 3T at the moment, that is helping you make the difference in both clinical and research excellence. So we know that MRI plays a key role as the diagnostic tool for a number of diseases, and it has unique imaging capabilities. For example, we heard a lot about diffusion, we heard a lot about functional MRI that no other imaging modality can provide. But really, despite a lot of development and MRI having already improved a number of lives, there's still a lot of things that we do not understand. There's a lot of clinical challenges that still remain, and we brought out SIMA-X as a tool for centers that really cannot take a compromise in their image quality, cannot take a compromise in their scan time, but really want to innovate, want to take that next step in order to address the remaining challenges, and this is where SIMA-X is making the difference. So what is at the core of SIMA-X? So at the core of SIMA-X is the gradient system. So the Gemini gradients with a 200 millitesla per meter amplitude and a 200 millisecond rise time, which is powered by two super powerful gradient power amplifiers and hydrocore cooling technology. And what that does is really for the first time bring into a clinical reality this gradient performance, allowing short duty cycle, allowing super short TEs, while giving us this short diffusion time and the high gradient amplitude. And there was a question asked this morning about, can we not just up the amplitude even more, right? So if we up the amplitude even more, we are getting into territories of peripheral nerve stimulation, especially with fast rise times, and we have to get to these high amplitudes as well. So there are inherent challenges in the physics of this with higher amplitudes. But as another thing, what the SIMA-X also brings to the table is the entirety of our clinical imaging tools, that is that is the deep resolve AI reconstruction techniques, that is the My Exam Companion, and that is the biomatrix tuning and sensing system that allows us to track the physiology of the patient. And in addition, giving you the entirety of our open platform, our open environment. The beginning of that being what we call Open Recon, which is our open reconstruction environment, and I talk about that a little bit at the end as well. So taking all of this together really gives us the opportunity to drive MRI and make the difference for patients by bringing research into a clinical realm to discover new insights. So in order to connect this a little bit, right, bringing this research and clinical together for those of you with children and possibly also for those without, taking a reference here from the hugely popular K-pop Demon Hunters, at least with my children. The main character is torn as she discovered, as she is meant to fight demons, but she discovers that she has demonic features in her. So a lot of her friends look at this very suspiciously, and they think, can someone with demonic blood really do the job there, fighting demons? But then what transpires in the film is that you can bring it all together, and when you bring it all together, you can still make it work. And I guess that's where the CMRX really comes together and really combines this clinical and research excellence now here at SNU in the backdrop of Seoul. And a really good example is when Chris Nguyen at Cleveland Clinic got his CMRX, he looking after cardiac imaging. He was really excited about being able to translate his research into clinical, but not only that, but really to do it at scale, right? Because there's no boundaries. It's a whole body gradient system, and you can really take next steps very fast. We already heard a lot about diffusion imaging today, but really, where do these gradients come in? So what we heard a lot about is that you can keep your TEs short, you can get to these super high B values, and in order to retain SNR over the echo train, you need short TEs, especially if you drive high B values. When we compare the CMRX in the top against what we used to be able to do with our magnetron Prisma, you can see that we didn't even get to B16,000 because the scan time would have been way too long in order to even acquire this. But you see already the signal fading at B10,000 with a TE of 114 milliseconds. So this pure SNR difference already shows you how important it is to keep the echo time down. But not only that, before the Prisma being the sort of the gold standard in terms of clinical gradient capability, the B10,000 scan would have taken half an hour. So it was beyond clinical realm. Now we can bring the B10,000 scan that gives us access into this regime of tissue microstructure in a scan time of 6.5 minutes. And I think this is this piece about clinical translation, where suddenly you come into this area of clinical realm using research technology much faster, and you can scale the adoption of research techniques into the clinical realm much faster. So, and this is really powered, a lot of it is powered by this new hydrocore cooling technology that keeps the gradient coils cool while scanning and allows us to keep the gradient duty cycle very low. So the CMRX has already received a lot of global adoption. We have over 50 installations worldwide. They're not all named here, but we're very proud of our and excited about our early adopters, especially here in Korea and at Seoul National University, of course. And Derek Jones, for those of you who know him from Cardiff University Brain Research Imaging Center, who onboarded a connectome system early on in the game, is really a neuro person. he said that the strong gradients are not only beneficial for the brain, but any area of the body where we have soft tissue and restricted diffusion. So they're going to benefit massively. And when we look at how the system is being used, then yes, a large proportion, just over 40%, use it for research only, but the majority is for clinical and research use combined. So key point being that this is as much a clinical enabler as it is a research enabler. Furthermore, I guess in the research space, when you look at the distribution of research interest, neuro is a large part, but in any MRI, neuro is always a large part. But we see, interestingly, that onco and cardio almost make up a third already, and then the rest being other clinical topics, and a big proportion with no particular ology specialism, but rather an all-around research capacity. So starting with looking at whole body DWI, right? Plasmacytoma, multiple myeloma, where you have to scan multiple stations across the entire body. Now doing this very fast at 2 minutes per station, and really with a nice seamless stitching of the whole body diffusion scan in only 8 minutes. This is a scan that would have taken before probably around the 15-minute, 16-minute mark, and would have been likely to incur a lot of motion. Zooming into a little bit deeper into the body, specifically the prostate, bioparametric prostate MRI of a 69-year-old man with a high PSA. This is a PIRADS 5 lesion. And you can see here that applying this high B value of 3000 lets you really visualize the tumor that is not as easily possible or as easily distinguishable from healthy tissue with the lower B values. And University Hospital in Bonn was one of our earliest adopters of the CMRX, and they used the scanner in clinical setting, but they use the gradients and have since changed from multiparametric prostate MRI, which is sort of the clinical standard, to biparametric prostate MRI, because they can now ramp up the B value in diffusion to the degree that the diffusion alone gives them enough information so they don't need to run multiparametric MRI, and they can acquire this data very, very fast. So that has allowed them to drop their scan time down from to a 7-minute scan and to a 15-minute slot time, where before they used to run at a 20-minute slot time. So that's a 25% reduction, obviously thanks to the amazing IQ with the CMRX. But they don't stop at the prostate. There's also many examples of exquisite multiple myeloma imaging, again applying high B values, but also liver with hepatocellular carcinoma, and all really with stunningly fast scan speeds. You can assume, I guess, a 3 millimeter slice thickness, but these are big coverages with super high resolution, even in the diffusion imaging, thanks to also a lot of the deep resolve. And here's an overview of a few other things that we can do with deep resolve. They're now internal images, so no patient images, no pathology on those, but just want to emphasize this power and insight that you're getting for the whole body complete protocol set. Hayes Deep Resolve, Vibe Dixon, also diffusion weighted imaging. I mean, the diffusion on the bottom left, the B800, almost looks structural, right? And this is a diffusion scan. So it gives us this ability to really zoom in to a lot of body examinations and apply diffusion in a way that we haven't been able to done before, but also the structural imaging is super high resolution at very, very doable scan times, where before it would have been 3 breath holds. Now we're down to a single breath hold with Hayes imaging, making the applicability of the technology a lot more abundant. Now, one more case is a case from Peking Union Medical College, thanks to Professor Langzhu. This is a 49-year-old male with obstructive jaundice and a history of abdominal bloating. So this was a suspected pancreatic head carcinoma, and thanks to the high resolution, the diagnosis is a rare autoimmune disease. So in the coronal and axial haze, you can see a narrowed but non-obstructed main pancreatic duct. So, and the Zoomit DWI then provides this sharply delineated hyperintense lesion in the pancreatic head. So, and after 4 weeks of hormonal therapy, the patient recovered. This article, if you find some of the QR codes there, they usually link to some of our Magnetum Flash articles if you want to look into the case more closely. Then again on body, a really nice paper from Malwina Molendowska from Lund University, where she looked this work was originally based on the connectome, where she explores how ultra-strong MRI gradients and advanced diffusion imaging give us much more advanced insights into microstructure, tumor conspicuity, and identification capability. So when you look at the figures there, which again are also published in our Magnetum Flash, the orange boxes representing the 300 millitesla per meter connectome system, really giving you a step change in CNR and in SNR, allowing you to see things almost in a virtual microscope kind of way, and different capabilities of resolving tissue. Another example here, last example from the body, a dynamic contrast enhanced. This is an example from Eva Women's Hospital, where you can see high B values up to B3000 applied in the breast, and then still seeing the lesion very clearly here, completely removed from background. So really, the whole body gradients playing out here. But of course, we don't stop there. This is a case of a 90-year-old female with a red and swollen first metacarpophalangeal joint, and it turned out to be an osteomyelitis with a subcutaneous access. So small field of view imaging with deep resolve, 3 minutes at a 0.2 by 2 millimeter in-plane resolution, and really giving exquisite structural detail again along that virtual microscope kind of fringe. But then high precision and high speed, very often powered by deep resolve, giving you this exquisite shoulder imaging, giving you exquisite small field of view imaging, super high resolution. This is 0.1 times 0.1 times 1 millimeter. So this is getting into 7 Tesla territory with a 3 Tesla system. So really the signal is there, and then deep resolve does the job in order to bring back a lot of imaging, especially in tricky areas such as the wrist in this particular example. But getting over to the brain, this is another internally acquired image I just wanted to share. It's an SWI, and I really love how clean the general image quality comes out on the system, and how conspicuous the vessels are at a 0.3 millimeter in-plane resolution, again approaching what people used to do on 7T. So you combine this with a flare, it will be perfect for multiple sclerosis identifications, really with confidence. So super high resolution at 0.3 millimeter in plane. Derek also said that where any disease where the cellular architecture is affected. So we spoke a lot about, or we heard a lot about microstructural imaging today. Brain tumors are the obvious candidate, but also multiple sclerosis, neurodegenerative diseases, dementias, movement disorders. There's going to be many benefits, and we've already seen many benefits. But what the CIMA X also does is it brings in a new biomatrix motion sensor, because as we get to more challenging diseases, we also see more challenging patients, and we need to facilitate the ability to scan those challenging cases. So this is why we introduced the biomatrix motion sensor, which is a software-based retrospective motion correction in a modified MP-RAGE sequence, and it detects head motion along 6 degrees of freedom and then compensates for that motion during image reconstruction. So this is a real example from Royal Melbourne Hospital in Australia, and shows what would have been non-diagnostic into a diagnostic image. So you can see the structure of the cerebellum here, which comes out clean and diagnostic, where before it wouldn't have come out like that. So this works by the biomatrix, the new biomatrix motion sensor, which was introduced with the CMRX, where a software-based analysis which is known in the literature as SAMA, detects motion along 6 different axes and can then immediately compensate for that motion during image reconstruction. Where we then can bring it all together. Here's an example from pre-surgical planning, from the South Australian Health and Medical Research Institute. I'm based in Australia, so I might be a little bit more glowing about the Australian examples. This is a dysembryoplastic neuroepithelial tumor here on the bottom left, where the arrow is. And the typical therapy is surgical resection. So they ran a resting state fMRI and a DTI in order to plan the surgery, and you can see nicely how that facilitated the access planning and helped preserve the surrounding structures to provide a very good, high quality patient outcome. But the CMRX obviously doesn't stop there. We've seen from our install base so far, some of the early adopter in Madrid. They look very, very deeply into Alzheimer's research. At Wayne State University, looking into susceptibility imaging, obviously their strong suit with ultra high resolution parallel reconstruction of multi-echo, which they call Supreme for multiple sclerosis. That's an ultra high resolution technique that is used to acquire quantitative measures, oxygen extraction fraction and iron deposition to predict cognitive impairment in MS and other types of neurodegenerations. So then we have characterization of axonal disease in patients with MS using high gradient diffusion, MR imaging from Susie Huang and the team at MGB, and Paris IBM looking at the direct mapping of human pallidus subthalamic pathways with diffusion MRI. So a lot of very interesting things coming out very rapidly from the community there, and I'm looking forward to what more is there to come. So after neuro, skipping over to cardiac. Again, it's a whole body. As much as it's research, it's also very much a clinical system. It has all the biometric sensor technology. So this is the beat sensor. This shows an example with a beat sensor. That's a cardiac sensor that's built into the cardiac coil. So you don't need to stick ECG leads on the patient. It automatically detects just by placing the coil the heartbeat and can then run a fully triggered cardiac acquisition. So this was an acquisition completely without ECG leads on the patient. Beautiful images. Here, a more clinical case, again from the site in Bonn, who used the system across the whole body. This is a 35-year-old male with hypertrophic cardiomyopathy and a septal scar after a TASH procedure. And the question there was, this is the high signal with the arrow in the LGE sequence, and the question there was, is there an outflow tract obstruction? Beautiful images, obviously, of the heart. But coming back to Chris Nguyuen's example at Cleveland Clinic at the beginning, a lot of people have been asking for a long time, have been tossing around with the idea of cardiac DTI. Now, cardiac DTI, yeah, a bit of a philosophical topic, a lot of ex vivo studies because it took so long. The heart obviously is not supposed to stop, so we won't find a still heart otherwise in a patient. So, however, now Chris has found a technique where he's able to get a 12-direction cardiac DTI in a beating heart. So this, for the first time, moves this, what was previously completely reserved for the research space, into a clinical domain. And I guess, understandably, this is where people like Chris will be getting very excited about the prospect of using the CMRX on a bigger scale. So yeah, and about this technique, he's published it. The gradients are obviously a key ingredient of facilitating this, but then it's not just pretty pictures. As patients get older, I think the Korean society is also on an aging demographic track. We have more people with kidney disease, and contrast-free scanning is becoming more and more important. So having a contrast-free imaging techniques that lets you look at the structure of the heart is and bringing that in towards a clinical realm is obviously becoming very, very important. Now, this is available on our C2P exchange platform. So keep that in mind, C2P exchange, because that's going to feature a bit more from here on, and that's the piece where research is being facilitated. So we realized the need for translational prototyping. So we heard a lot about AI today. We spoke about it at lunch, right? A lot of the students are interested in AI. So with this growth of machine learning techniques and computational resources, fast adoption is desired, right? To really see what sticks, but also really to leverage this in order to enable faster workflows and more detailed evaluation. But in order to do this, translation of research to the scanner is key, right? Because otherwise it will be a pretty paper, but we will not see it in the clinical domain. And the traditional workflow is offline, right? The student does something, takes the images of the scanner, does something offline, but that is not scalable to greater volumes of data, greater volumes of patients very easily. So in order to improve this, we are thinking about the possibility of inline processing to accelerate the development, and that would be critical for facilitating clinical evaluation and effective translation of this research. But how does it look? How does it look today? The clinical world is this, and then the research world is that. And normally what the PhD student and everyone else, the researcher, faces is a big wall between them because they don't talk. Yeah. So that can be hard. Yeah. That is good enough. Yeah. Because we can take images of which often looks like that. We export the data, we take them off, we take our USB stick. Even if we have a network connection and maybe make it a little bit more elegant, it's slow. And it always requires export data conversion. Manual errors is very tricky. So you need external hardware. You can't inline use. You don't have fast adaptation to change in circumstances. And if we want to get it back into the clinical domain, it requires re-importing, which is often simply not occurring, right? Because the data then end up on the researcher's computer and they never make it back to a clinical researcher. So in order to change this fundamentally, we've introduced OpenRecon. And OpenRecon overcomes these challenges by allowing our scientific customers to run their reconstructions directly at the scanner, which then essentially becomes the computing platform. In addition, you have direct access to the user interface where you can implement your own parameters. So you don't need to go around and find a hard way in order to change this. You can rerun the reconstructions with a different parameterization directly on the scanner. And this is how it works in a nutshell. So we export data from the Siemens image reconstruction pipeline in a standardized ISMRMD format. So that's a format that the ISMRM community developed from here on, called MRD format. It's standardized, and then you can import your Open Recon container. You can in whatever language it's based on Docker, and that uses the computational resources of the scanner reconstruction system. So it runs on the existing Mars reconstruction system hardware, and it uses, because using Docker, it's completely platform independent, and especially what is important in the past, it was always dependent what software version is the scanner on. This will be independent of the scanner software version, meaning that you can find another Siemens scanner that supports this and still run the same Docker container without recompiling and looking at the dependencies of the software. So that allows to easily share apps with others. And that's also why we've added now Open Recon to our Magneton community. And that's the place where you can discuss, share, and also learn together with other Siemens, with our community of like-minded Siemens users. So C2P, I showed you before. This is where Chris Nguyen's cardiac TTI sequence lives. For those of you who don't know, C2P stands for, it's actually C squared P, so it stands for Core Competencies Program, and it is an online platform where our collaboration partners share their research sequences. You can go, you can access it online, you can download, you can put your own sequences up there, both on the sequence side, but also now on the Open Recon side for the first time. So both image reconstruction as well as pulse sequence prototypes can be found there. You can look what's on the menu. You can share your own, and we would very much love to have more of that great science that comes out of Korea on that platform, obviously. The Magneton forum then complements this. All of the SDKs, the pulse programming, also the image reconstruction, Open Recon SDKs are available there. There is discussion opportunities in order to learn, network, and really share. So to give you some examples of how this works in the real world, we even use Open Recon internally. This is an example of a deep learning-based inline bias field correction in order to reduce the B1 and all sorts of magnetization-induced inhomogeneities in the image, where we now have a deep learning method that runs inline. And in order to keep it completely independent of software baseline and scanner, it was put into an Open Recon prototype that what we call as a works in progress or WIP sequence in order to make it easily transportable. But then also we have customers, and this is an example of a brain imaging pipeline from Benoît Béranger from Institut de Cerveau in Paris, where he put the ANS pipeline entirely into an Open Recon container. So you can now, instead of taking the data offline and using it on your own machine, you can now use ANS, and you can simply download Benoît's implementation, Benoît's Open Recon container, put it on your scanner, and use ANS directly on the scanner with full parameterization. So that gives you the access to bias field correction, denoised images, and multiple skull scripting and based tools. So yeah, gives you access to immediately all of the results on the scanner platform, because once the data are processed by the Open Recon container, they go straight back into the image database, and you will be able to look at them on the scanner. And if something was wrong, you can even rerun the reconstructions on the scanner itself. So with that, we've really taken massive steps to make the SEMA X as a connecting element to our global research community, supporting collaborations and knowledge sharing, multi-center facilitating, making it easier to do multi-center studies with the platform, and by our open tools, and there's more to come, have a foundation through our C2P exchange that gives you access to the entire community of our Siemens users. With that, I was trying to. I hope I wasn't speaking too fast. I was trying to make up a bit of time. I think I landed on point. Thank you very much for your attention, and yeah, have a great night.
Thank you, Dr. Schmitz. We have some time for questions.
Thank you for a brilliant talk. I have one question first about the last example from ICM. So with Open Recon, if you have, say, you run a T1 sequence, run a T2 sequence, do a flare, they're usually separate sequences.
Yeah.
Then can you sort of combine them, input Open Recon? So I think, is that capability already there, or?
No.
You know what I'm saying? That's why I was wondering.
Yes. It's a great question. So, no, the access to any prior scans is currently not available in the pipeline. So if you want to then say, technically it's so theoretically it's possible, but you would have to put it somewhere on the hard disk file output and then gobble it back up in order to use it for subsequent reconstruction. So at the moment it's not trivial.
And then, so how did the ICM team do it? You know, they have, looks like, they run each one separately. They should have a T1, they do T2. Okay.
Yeah.
Probably not. Okay. Thank you.
Thank you for your informative talk. I have not experienced the SEMA-X yet, so I'm wondering if there are something like side effect, like dizziness or vomiting attributed to the high, ultra high gradient, as in the case of 70.
Right. So the side effects, as Professor Fukunaga explained, the side effects mostly come from the static magnetic field. So the static magnetic field of the SEMA-X is also 3 Tesla. So you wouldn't have any such side effects with the SEMA-X just based on it, because it's from that perspective it's a standard 3T clinical system. What I was talking about earlier is with the extremely high gradient amplitude and fast RAM times, what happens is you get induction in peripheral nerves and peripheral nerve stimulation. But our system has a peripheral nerve stimulation model, and if the system would overshoot some of these peripheral nerve stimulation thresholds, we wouldn't be able to have it on the market. So the system is tapered in order to avoid any peripheral nerve stimulation based on a very sophisticated body model. And that's what I was saying before. So you can't just arbitrarily up the gradient amplitude or the ramp time because you're going to be violating peripheral nerve stimulation thresholds even easier. So the SEMA-X from a whole body perspective is really where we landed after the experience with the connectome system that has a 200 millitesla per meter gradient to be a safe space where you can fully utilize this gradient amplitude.
Dr. Zahin?
Yeah, I just want to follow up on that one. I just remembered. So I think when you turn the 3 axes on simultaneously, you can technically get to 350, which is
358 or something.
Square root of 3, right?
Yeah,
the idea is your concern for the peripheral nerve stimulation is accounted for all 3 on the same time as well.
In real time.
Right.
In real time, yeah.
Yes,
so the sequence execution is looked at against the peripheral nerve stimulation thresholds and would be tapered if necessary in order to avoid peripheral nerve stimulation.
But what I meant is the assumption is even when all 3 on at the same time.
Yeah.
That's okay.
Yeah.
One other thing, in your example picture, I think if you don't know, you can go back to the one showing the Prisma and
Yeah.
comparison, which is, I think I'm aware, I just want to quickly follow up one of the question in the brain example, which I think really good illustration. Oh, yeah, if you go, I think it was that one, if you can maybe blow it up. If you, maybe next one, perhaps? This one. So you can notice that there's a brain distortion due to susceptibility that's also quite distinct. Is that something to do with the system setup, or
You mean less on the? You mean less
it looks
on the
less in the
CMRX?
CMAX, at least for this example.
Yeah.
What would you say that?
I mean, this is gradient nonlinearities, right? The distortions.
Just
So
one-
it's better gradient.
So that's also better as well in that
Yes.
sense.
Yes.
Okay.
Yes.
Yeah, but
So
you
the
know,
precision that was necessary in order, and that's why that makes these Gemini gradients so special, right? The precision that was needed in order to run them fully simultaneously with two separate gradient power amplifier, there needed to be a very, very high degree of precision in order to achieve this function effectively, and that's
Yeah.
why you will see, and we've seen phenomenologically. I mean, I think there was a question this morning. Is there any benefit in susceptibility weighted imaging with CMRX? So technically, the gradients don't play a big role in susceptibility weighted imaging other than flow compensation. But we've actually seen with the gradient linearity that we have on the CMRX system that the SWI visually looks very, very nice.
Yeah, and actually that's one of the things I couldn't mention for the that's really good, helpful. I think duty cycle also is dramatically better.
Yeah.
Because of cooling. So
you see the
yeah.
TR.
That's amazing.
It was 21 seconds on the Prisma. And the Prisma is an absolutely amazing machine. Yeah, it was recommended by the NIH for the human as the only scanner for the Human Connectome project. So we're not talking a backyard kind of scanner. We're talking a state-of-the-art 3 Tesla system. But the CMRX now really lifts it to a next level with this duty cycle.
Thank you.
Thank you.